All right, everybody, welcome back and happy Friday. We are basically going to be wrapping up our week number 3 here today. So at the end of class, we'll be about 75% of the way done, which is very exciting. We can see how fast these classes move in real time here. Only 1 week remains. As a reminder, we do have moderators in the platform, so should you have any questions about the actual course content that we're covering in real time, or if you just have questions about anything else aviation related or basically about check ride prep, throw it in the comments and we'll do our best to get to those. As a reminder, there are a number of FAA test questions throughout the aviation weather section, so when these FAA test questions come up, just remember that there's a little vote button in the lower right-hand corner of the live chat, and it will actually appear once the question is live. Right now, you should not be able to see anything, but right beneath where it says the send, you'll actually see that blue vote button. When the test question appears on the screen, just remember to use that vote function. Do not answer in the chat. Don't give away the potential right or wrong answer to your fellow students. And we'll be just fine moving forward. So with that, let's go ahead and see what is on the agenda for today. Like I said, I don't have too many announcements. This is class number 9 on aviation weather. And if you remember, just 2 days ago, we were talking about radio navigation, and I know a lot of people have trouble with that topic. We never made it all the way through, so we basically stopped right where we finished the VOR section. So the first thing that we're going to do obviously today is pick up where we left off, which should be the GPS section. We'll basically talk about the components of the GPS. We'll talk about the 3 segments, the space segment, the control segment, and the user segment. We'll talk about some of the GPS terminology that you need to know. We don't do a deep dive into GPS, so we're not going to talk about WAS, LAS, GBAS, or any of these others. If you end up taking our instrument program, you'll learn far more about it, but it is kind of an interesting topic overall. For those that are struggling with the test questions, I understand that the test questions can be rather challenging for the VORs. Keep in mind that when you guys are looking at those, there's only about 30 or 35 FAA test questions within this section. So I would encourage you to take the test once or twice, the quiz from yesterday, once we complete the lesson, right? So if you see the questions a few times, I guarantee you won't have problems with them in the future. And remember, if you are still struggling with them, take a screenshot. If you still don't understand why, throw it in either the Facebook group and we'll see if we can explain it, or put it on Ask a CFI. Either one works there. So I anticipate probably spending about 20 to 25 minutes with GPS, and then we're actually going to move into today's lecture material, which is going to be on aviation weather. And the way that this class is designed is we break it up into kind of 2 different sections. The first half of the class is dealing with aviation weather theory, what causes weather. For those that want to throw it in the chat right now, what do you think the primary cause of weather is here on Earth? And we'll talk about that in a little bit once we actually get to that section. But if you know it, throw it in the chat and we will discuss here in about 20 minutes once we start that topic. With the aviation weather theory, we're going to be talking about all the different terminology that you need to do, that you need to know: temperature, dew point. We'll get into a little bit of density, altitude. We'll cover the rest of density, altitude in our performance section. We'll get into temperature, inversions, cloud types, the ingredients for a thunderstorm, different types of fronts, different types of icing. And then the other half of the class, we're going to spend more on the practical aviation weather side. So we're going to be talking about the resources that we have as pilots to basically figure out what is the current meteorological conditions, and those are known as METARs. What is the forecasted conditions, which are known as TAFs, terminal aerodrome forecast. And then we'll also move into some of the weather charts, AIRMETs and SIGMETs, as well, and also PIREPs. Now, we will most likely not get through all of this today. The aviation weather section is a rather lengthy section, so we'll do as much as we can. And once again, if we end up, wherever we end up stopping, we'll basically pick that up next week when we start again. For your future planning, just keep in mind that we'll cover whatever remaining material is on basically either Sunday or Monday, whenever our next class starts. And then what will end up happening is we will get into aircraft performance, which will be the next class. And we'll also talk about weight and balance. The middle part of the week, we're going to be talking about flight planning. So we're going to try to put everything that you've learned so far: aviation weather, performance charts. We'll also look at some of the regulations that you learned and a bunch of other things, kind of put it together in a large scenario and figure out how to actually plan a flight from point A to point B. And then at the very tail end of the week, that is our very, very last day of class. So just keep in mind that there is still quite a bit of material that we have to cover. The very first part of the class is a little bit of admin, how to close out the course, how to get your credits, how to get your endorsement, how to take the final test, etc., etc. And then we actually have a lot of safety related material that we have to cover that will actually be on the test as well. So you don't want to miss that either. But we are closing in just 4 short lessons, including this one right now, before we wrap up for the end of this course. As a reminder, you should have received an email invite from us to leave either a Facebook or Google review or whatever your preferred platform is. It's not really for us, but it's to let future students know about the course and what tidbits you can provide to them in terms of how to be successful in the program. As a quick reminder, next week, basically a week from today, you'll receive a confidential course survey. And they are completely confidential. We just want to know what went right, what went wrong, what you guys like, what you didn't like. And we do go through those with a fine-tooth comb. Pretty much 80 to 90% of our changes here in-house are actually from your comments. And a lot of that has really shaped what we do. Everything from the mobile app on multiple platforms, being able to stream the live classes, changing up the test questions, and a bunch of other things. So including one of the big requests that we've had over the last 2 years is more classes. So we used to only do 1 class per month, and now we've expanded that to 6 classes per month for better timing for everyone. So it only takes a few minutes, and we encourage you to fill out both if you can. And you'll probably see another reminder here in your inbox over the weekend as well. Okay.
Just like we do for every single class that you guys attend, we'll cover what is the catch. Hopefully by now, as we move into week number 3, there is no catch to this class. You guys have had access to the live streams in multiple locations, including YouTube, Facebook, and also on our website. Same thing goes with the actual recording. So if you couldn't make the live class, you could always listen to the recordings after the fact. You also have access to any of the recommended homework documents, handouts, the quizzes after each lesson. Also, the final exam, which will become available on our very last day of class, which will lead to the endorsement provided by one of our certified flight instructors here on staff. So we don't charge for any of this material, so there is really no catch to this class. If you don't believe us on the 3rd week, hopefully you'll get it by the 4th week here. The only thing that we will do, as I've always said, and we'll remind you of this of every class period so there are no surprises, the free access will terminate at the end of class. So our very, very last day of class will be Friday, October 14th. Then we give you 5 additional days to watch any videos that you may have not seen or anything that you need to catch up on. In addition to that, on Friday, October 14th, that is when the final exam becomes available to everybody. We usually open that up about an hour after the start of class because remember, there is quite a bit of material that we're going to cover on that very last class that will still be applicable to the final exam. In order to get your FAA written test endorsement from one of our certified flight instructors on staff here, all you need to do is watch all 12 of the classes. It does not matter whether it's live or recorded, mix and match. Also does not matter which platform that you are listening or watching on. And then finally, you need to take that final exam, which is a total of 60 questions, and you get 2.5 hours. It is timed. We do our best to mimic the actual FAA exam to the best of our ability, that is, and you have unlimited attempts to get an 80% or higher. During that 5-day period, I've seen students take it upwards of 20 to 30 times. Even if you are scoring an 80 or 90%, I would encourage you to retake it a few times because every time you take it, it's going to give you a new set of questions. If you've been following along with all the lesson quizzes to date, you should have no problem when it comes to the final exam because the final exam is going to pull 60 of those questions in different subject areas, which are the exact same questions that you've already seen on your lesson quizzes. So as a reminder, just go ahead and keep up with the lesson quizzes. If you haven't been working on them, while it is not a requirement, it will be very beneficial to see how the FAA presents these types of questions. And the answer choices as well. As a reminder, occasionally we see emails from students saying that I've taken the lesson quiz a few times and some of the questions are exactly the same. They are similar, but they're definitely not exactly the same. Sometimes it might be the same question, but different variety of answers. Sometimes the FAA will ask it in a slightly different way. So just kind of keep an eye on that. The reason why we include all the potentials out there is that so when it comes to your actual FAA exam, there's no surprises. So anyways, 5 days after our last day of class is going to put us on Wednesday, October 19th, and that is when we shut down the free access at 12 noon Pacific Coast time. So just keep in mind that all the videos will come offline. The course will basically be wiped out. So if you have any, obviously if you've received your endorsement, your certificate of completion of the course by that point in time, that is yours for life. We don't delete those. That remains in your profile. It's also emailed to you as well. The reason why we do shut down the class, as we've always said, is that it gives us a higher completion rate. Right now, we are at 95.5%, almost at 96%. If we left the course open year-round, we would not see the numbers that we do. We've had about 100,000 plus students enroll in our program over the course of the years, that is. And we've had great success by, holding everyone's feet to the fire. As I've always said, anyone who started with us on day one, we want you to finish at the end of class. And, myself and our instructors on staff and our support staff as well, will do our best to help you out, answer any questions that you have along the way. With that, here is my public service announcement. I'll try to keep this short and sweet. As a reminder, if you do need more time or if you like the way that we teach, you do have the Private Pilot Lifetime membership available to you, so that includes the Private Pilot Ground School. The nice thing about Check Ride Prep is we're the only flight school out there that actually teaches live, and we teach these classes also for our members behind the scenes in a more slow pace. We basically teach these classes every quarter, so instead of taking the classes every, within a 30-day period, you can actually take it over a 12-week period. In addition to that, we also professionally record these classes, so you do have the ability to watch these lessons. There are no breaks. There's nothing like that. And when we look at it, instead of basically watching a 3.5-hour lesson, they're basically 60 to 70 mini lessons, depending on the course that we're looking at. We keep these all up to date, depending on any regulation changes or any type of changes in the curriculum that the FAA dictates. In addition to that, you have unlimited practice quizzes and exams. You've probably noticed by now, every time you take a lesson quiz, the quiz questions and also the answers are basically randomized, so that way you don't get used to memorizing the test question. And at the end of the day, it's really beneficial. Some schools I've seen out there, they basically don't have that ability. So what they do is they give you 8 or 10 final exam. And unfortunately, the final exams are static, meaning that if you take, exam number 1, the questions will always be in the same order. The answers are always going to be in the same order. Our system actually randomizes the whole process to, further prepare you for the FAA exam. You have 24/7 support from our team of instructors and our staff here. You'll also have the ability to get the FAA written test endorsement at any point in time. So the date that I mentioned previous to this, you could disregard if you know that you're going to need more time. Same thing applies to the FAA wings credits. And then you'll also have access to all of our past webinars, and we do live seminars typically once a month. You'll be invited to those. As a bonus, you'll have access to a separate course, which is our Private Pilot Flight Maneuvers course. This is basically all the different flight maneuvers that is kind of outside of the ground school. We don't have time to cover them here, but the Private Pilot Flight Maneuvers are basically all of the required flight maneuvers that you're going to be doing and working on with your certified flight instructor once you find that individual or flight school. And finally, you'll have access to our PDF guide, the Private Pilot Companion Guide. So this includes basically all of the handouts and the documents, the testing supplement, note areas, and a lot more information. And it's basically organized in the 12 lessons of how we teach them. It also has 120 pages of course notes from certified flight instructors who have gone through our program A to Z and basically put those in there as a reference in order to simplify the process there. So that is it for my public service announcement. Like I said, let's go ahead and move into the course material for today.
All right, so what was left over is we finished the GPS section. We finished the VOR section. Be a little too premature to finish this section. And I know there's a lot of questions with the VOR. And, some people were saying, well, how do I know what radial am I supposed to use? And I think the easier way, I was kind of thinking about this afternoon, and, if you have a GPS, keeps going with GPS, a VOR facility, right? So we have a VOR ground station. And that is, we're always going to treat the top of the page as north and the bottom of the page as south. And we obviously know that radials only go out or outward from the actual station itself. Okay, so we'll call this the Camarillo VOR. And this would be the 360-degree radial, and this would be the 180-degree radial. And everybody kept asking me, or I kept seeing questions, if my airplane is here, how do I know what to put in the OBS? Okay, so you do know at this point, if you're flying to a VOR, and we were in the airplane that's as drawn right here, we definitely want a 2 indication, right? And if I was obviously in an airplane over here, I would want a from indication because I'm actually flying away from the Camarillo VOR, and that is supposed to say FM or from, okay? And the question is, you know, what am I supposed to put at the top? That was kind of where people were a bit confused. And I think if I'm in aircraft A here and I am looking at, and I am trying to basically fly northbound, and my goal is to get on the 180-degree radial, as you see here. In this case, you always want the reciprocal or the radial on the opposite side of the VOR. So in order to not get reverse sensing, and if I was in position A, I would actually put 360 degrees at the top, and then 180 would be at the bottom, okay? Now, if I'm in aircraft B here, and I am trying to basically intercept and track the 360-degree radial, then my only option is to basically do 360, and that would also lead to 180 down here, and that would give me the from indication because I'm basically flying away from the VOR, okay? If I were to reverse this here, and I was in this position, I'll call this aircraft C, okay, and here is that CDI needle. I know that I'm flying to the VOR, so I definitely need a 2 indication. And, you know, I'm trying to track this 360-degree radial here, but what I need to do is I need to track the reciprocal of that, what's on the opposite side of that VOR, which would be 180 degrees, okay? So think about it this way. If you're flying to a VOR, you're going to track the opposite radial, or basically the reciprocal radial, so it doesn't really matter what it is. And you can add 180 or subtract 180, or you can do +2, -2. If you're flying away from a VOR, then you're just going to select the radial that you're basically utilizing to fly away from the station and put that at the top in the OBS setting. So hopefully that might clarify it without actually trying to confuse too many people, but I think that might be an easier way to explain it, since I know some people were having some trouble with you know, trying to figure out what am I supposed to put in or on the top of the OBS for some of these questions. All right. All right, let's go back to the GPS system. So this is the global positioning system, and this is just a simple concept, even though it's kind of complex. All of these systems, in terms of the VOR, the NDB, and even the GPS, are all going to be based off of radio navigations, and basically we know where, you know, each one of these GPS satellites is at any point, and we can be very, very precise with the information. So each of the satellites themselves carry a very stable atomic clock, and they're synchronized with each other, and then they're also basically synchronized with a ground station using a ground clock. And then anytime that there's drift, anytime that the time changes in any one of the satellites, they're going to basically correct that daily using that ground station to make sure each satellite has the exact same time down to the millisecond. And we also know the exact satellite location basically 24/7. Now, each GPS satellite is going to continuously transmit a radio signal, and that signal is going to contain basically information about the current time and the data about its position. And what that's doing is you're going to get either somewhere between usually about 4 to 5 satellites that are going to send that information to the receiver in the aircraft. And because we know the speed of radio waves, which is very close to the speed of light, we know that if it took, you know, I don't know, I'm just going to say a second because I don't know what the subseconds are there. Let's assume it took a second to send that data from the satellite to your receiver there. Then your receiver can then basically compute the delay in terms of when was it sent versus when did that signal arrive, and then figure out where were those satellites when that signal was sent, okay? And that's really what your receiver is doing. Now, with the GPS system, there are 3 different segments. The first one is known as the space segment. We call these the SS, which is actually composed of 24 to 32 satellites. And these are all located in medium Earth orbit. So this includes basically the payload itself, all of the instrumentation, and boosters as well. In the event that the orbits actually decay and they get closer to Earth, then what they'll do is they'll bring those satellites offline. They'll use the boosters to bring them up to whatever the appropriate altitude is that they should be orbiting Earth. As of 2 years ago, on 2019, there's a total of 32 satellites within the GPS constellation, and 27 of them are going to be used at any given time. The rest are basically allocated as standbys. Now, this is important information at the very bottom of the screen. You will see a couple FAA test questions relating around it. And very simply, you need a minimum of 3 satellites in view of your receiver in order to basically compute a 2D position, meaning latitude and longitude. Where are you on anywhere within the Earth? You need a total of 4 satellites in view to get a 3D position, and that could be latitude, longitude, and altitude. And then you need a total of 5 satellites to basically have something known as RAIM, which is Receiver Autonomous Integrity Monitoring, and we'll talk more about that in the future. The way that I used to always remember this was I used to just write this down, basically 2D, 3D, and then RAIM. And you just kind of add one more to the number. So if you need 2 dimensions, then it's 3 satellites, 3 dimensions, it's 4, RAIM is 5. So whatever is going to help you to kind of remember how many satellites you actually need to figure out your actual position. So on the ground, we have this group called the Control Segment, and this used to be run by the Air Force. I still do not know, I haven't gotten confirmation if the Space Force question mark is taken over or not. But either way, it's either the Space Force or the Air Force. The Control Segment is made up of 4 different components. The first one is called the Master Control Station. This is really what monitors the satellites and the signals, and it also basically resets any of the time should there be any drift from the master clock. There is an alternate master control station if something happens to the primary. We have 4 dedicated ground antennas, which are basically located around the world, and also 6 dedicated monitoring stations, which are also around the world as well. That little golf ball pod that you see there was one of the older ground monitoring stations that was used to basically, know exactly where these satellites were at any given time. And finally, we have all of us. This is the user segment. So the user segment makes up hundreds of thousands of US and allied military users that use the GPS positioning system. And then we have hundreds of millions of the rest of us, right? So as we know today, we have GPS in our watches, our phones, our cars, our computers. Almost everything has a GPS chip in it. It is a fantastic technology to use. I remember when these came out in the early 90s, even though GPS was around for a while, even in the early 90s, this was not necessarily a tried or trusted system. In 2001, when I started my flight training, we had a very basic GPS system. It kind of looked like a Pong game. It just had a green screen with basically green letters with a black screen behind it. And I remember the CFI was like, don't even look at it. Don't touch it. We don't trust it. We're still going to fly with VORs. And now, 20 years later, we are, highly using GPS. It's far more accurate, and it's definitely more proven than what we originally realized. Within your receiver, it's going to have some type of antenna, and then it's going to be tuned to the frequency of whatever the GPS satellite frequency is. It will have a receiver and a processor, and then it has a highly stable clock. It's not going to be an atomic clock, but it usually has a crystal clock within it. And the GPS receiver will monitor multiple satellites, and then it solves equations. Remember, the equations are, when was that signal sent versus when did it arrive? And then it can basically figure out in real time, where was that satellite, orbiting at that given moment that transmission was basically sent? And then where was the aircraft when it was received? And that's how it computes your position. At a minimum, you need 4 satellites in view for the receiver to compute the unknown quantities, so 3 position coordinates and the clock deviation from the satellite time. There's also traditionally a display nowadays. These are pretty fancy, so they've definitely come a long way. It will, within the utility section or basically the auxiliary section, depending on the manufacturer, it will tell you how many satellites are in view at any given time. In the early ones, early GPSs, they were really only limited to receiving 4 or 5 satellite signals at any time. The newer ones, really anything past 2005 or 2007, they're typically going to have 12 to 20 channels. And if you were to look at how many are actually in view, most of the time you guys are not going to have a problem. It's usually going to be 10 or 12 satellites in view at any given time if you're anywhere within the United States. All right, so let's go on to this RAIM, which is that 5 satellite minimum, and we'll talk about why it's important here. So this is the G1000 that you guys see on the right-hand side, and if you were to go to the aux menu and basically go to the GPS status, which is the 3rd page of that menu, it's kind of like a sub-page, what you would see is you would see your compute RAIM function, and then each one of these bars is basically representing the signal strength of all of the different satellites that you actually have in view. So we can see that we only need 4 for a 3D position, and we need 5 for RAIM, but we can clearly see that we've got definitely a lot more than 5, which is the minimum, and this is usually what we would expect to see. The compute RAIM function will basically allow you to do a RAIM prediction. So, and what you would do is you're basically going to put in where you're going. So if your final airport is here, your arrival time, your arrival date, and then you would basically click this compute RAIM, and it would say RAIM available 99% of the time. I've only had it say unavailable once. But RAIM is the capability of the GPS receiver to perform integrity monitoring on itself by ensuring available satellite signals meet the integrity requirements for a given phase of flight. RAIM alerts pilots immediately, and I've always put this in red because students don't really understand this. I usually see this with instrument students, and the examiner asks, why are you computing RAIM? And the best answer students can come up with is, my instructor told me. This is the more important segment here, okay? So fault detection is critical because delays of up to 2 hours can occur before erroneous satellite transmission is detected and corrected by your friends in either the Air Force or whatever the Space Force is from the satellite control segment, okay? So if you can imagine if there was any type of time drift, or it couldn't necessarily compute your correct position, even if it's off by a mile or so, that is fairly significant if it takes them up to 2 hours to basically correct that false information, right? And 2 hours for most of us in GA is the entirety of our flight. And this obviously comes into play a lot more as you start getting into instrument flying. Can you imagine being in the clouds and you're trying to execute an approach to an airport and you can't see anything around you? You're in this nice white snowball. And if you're relying on that GPS to execute an approach and it happens to be a mile off, there could be a mountain a couple miles in your path instead of a clear path all the way down to the airport. So that's the purpose of RAIM. You would compute RAIM. Now for you guys, you do need to have the 5th satellite in order to have RAIM. So basically, if you click on compute RAIM and for whatever reason it says RAIM is unavailable, then you should not continue flying using the GPS system. What you'd want to do is just use a different form of navigation. So for you guys, you would probably use pilotage, right? Looking out the window and seeing where you are versus on a map, and also dead reckoning. Or you could also switch to radio navigation for VORs as well. So any of those others. That's the reason why it's always important to back up these systems. We're not going to get into WAS receivers or anything like that. That's in the instrument class, but WAS is basically, I saw that question earlier. WAS is basically the GPS signal, but it's a little bit more refined because it uses a ground station to basically send out a correction. Now, the WAS receivers are a little bit more expensive. In order to utilize a GPS, though, it does have to be IFR certified and actually panel mounted in your aircraft. You cannot just grab a local, a VFR GPS, and it can't be handheld. You can't use ForeFlight. Any of that stuff is all for situational awareness. It is not for use for actual primary navigation. Okay. All right, so as I said, this was like my old one. You can imagine these white letters here were actually green. This was like one of the original Garmin GPSs, and you could see that it's a little bit more old school. What most people are used to nowadays, or what you guys see in the lower right-hand corner, these are the Garmin 430s. They also made them in WAS versions, and then they had the 530s, which are actually a little bit more expanded or larger screens. And these you're going to find pretty much everywhere. There was 20,000 units made, which is quite a lot for aviation. And what you can see here is this actually mixes a GPS with a comm unit and also a navigation radio as well. And what you guys see here is this is the digital CDI representation. So that line, that vertical line, is basically your CDI. And effectively, your full scale is 1 nautical mile to the right and 1 nautical mile to the left. And that green triangle that's basically pointing up is the 2 indication. And what it's going to tell you is it will give you position information in terms of this is someone executing a GPS approach for the instrument stuff, but they're basically between two waypoints. They're past the ILO waypoint and they're coming up to DAC-B, and they're going to be about 4.88 nautical miles from DAC-B. That is their ground speed. We also have the estimated time en route, so 2:59. And the two numbers that I always like on my screen are basically your desired track and your track. And then we'll talk about what does desired track, and bearing just after we answer these questions here. All right, so let us move on to a couple FAA test questions. I'm going to go ahead and close out the original poll. So 73% of you were so excited about weather. That's awesome. Go to this one. How many global positioning system GPS satellites are required to yield a three-dimensional position, latitude, longitude, and altitude, and a time solution? Is it 5, 6, or 4? I like it, BR. So if the GPS basically craps out, then just stop using it. Yep, exactly. All right, first third of the class is in. Looking good so far. We've got a little over 50% now. Anybody going to go flying this weekend or do anything fun, whether it's flight training or anything non-aviation related out there? All right, about 75%. Waiting on a few stragglers. Driving a Simboni rock concert. Awesome. Guitars. First cross country. That's awesome. And some flying. IFR. Perfect. You're going to fly a kite. I like it. It's nice and cheap, right? All right, let's go ahead and take a look at it. We got 20% with A, just a handful of folks with B, and the majority class with the correct answer, which would be C. So remember, don't let this time solution throw you off. Just remember that latitude, longitude, and altitude. So just remember that you could write it two different ways. So sometimes I'll just write it this way. This would be how many satellites you have. So 3, 4, or 5. And then very simply, this is basically 2D. 4 satellites is 3D. That's the reason why it's the answer. And 5 satellites is RAIM. Okay. Whatever is easier for you guys to remember, or just remember that you need one more satellite than the dimension. So if it's 2-dimensional, you need 3 satellites, 3-dimensional, you need 4 satellites, and then RAIM is that final one. All right, let's go ahead and take a look at that RAIM question here. Bring this one up. If receiver autonomous integrity monitoring, also known as RAIM capability, is lost in flight, is it A, the pilot may still rely on GPS-derived altitude for vertical information, B, the pilot has no assurance of the accuracy of the GPS position, or C, GPS position is reliable provided at least 3 GPS satellites are available? Long Beach Grand Prix. I didn't realize that was going on this time of year. And riding the Harley before it snows. Awesome. Good advice, Lori. Pick the FAA answer. Yep, remember, this is what the FAA wants you to answer. Got the first third of the class in so far. So the time solution is just what is the time of arrival, which is called an epoch, EPOCH. It's called an epoch. and it's basically the time that that transmission left the satellite and the time that it was received by your receiver. There's some type of delay, and we know how fast a radio signal travels, so we can figure out if it took us 5 seconds for that radio signal to travel from the satellite to your receiver, which is, I'm just giving you a larger, way larger number, then where was that satellite 5 seconds ago in the past when it was sent? So that way the computer can basically figure that out. That's the time solution. The reality is you're talking about, like, I don't know, milliseconds delay. It's really not much. All right, let's go ahead and look at this one. We've got 3% with A, 70%, 71% with B, and about 26% with C. So remember, we do want to go ahead and use the FAA, what the FAA wants us to answer. And really, if this does happen and RAIM capability is lost, then you should not be utilizing it for any type of navigation, okay? And the reason why, too, is that if you think about it this way, we said that, in order to get, a 2D position, you just need 3 satellites, right? And a lot of people will guess C. And the reason why that's incorrect is, imagine that those 3 satellites are sending you bad data. So maybe those satellites the time is not matching the ground station, and it's giving you information that's completely inaccurate and erroneous. And if you have 3 satellites or even 1 satellite of the 3 that's giving you bad information, then you don't want to rely on the system whatsoever, okay? So it's not just RAIM is not just checking, do you have 5 satellites in view, but it's also checking, hey, the data that's being sent from these 5 satellites, is it accurate or not? And if it's not accurate, you wouldn't use it, right? So think about it that way, and that's the reason why B is the correct answer here. Okay. All right, good job, everybody. Go ahead and take a look and move on to the wonderful world of weather. All right, so with aviation weather, like I said, first half of the class is going to be basically weather theory, and then the second half of the class will be the practical side of things. A couple of references for you guys. If you guys are on YouTube or Facebook, just look in the description section, and I threw this website in there. For the rest of you on our website, just beneath this live stream under the links, I believe, something like that, you'll see aviationweather.gov. This is a really good free site. This is basically from the U.S. government, and it basically compiles a number of aviation-related weather reports from NOAA and the National Weather Service and a bunch of other organizations that put out these things specifically for aviation into a single resource. So this is just one method. There's probably 100 different websites that you can get the information from. Ideally, the best answer, if it ever comes to a check ride, is where did you get your weather information? I would prefer to say some type of government site, whether it was the Aviation Weather Center, or more appropriately, I pulled I basically pulled a pre-flight weather briefing from like a flight service station. And we're going to show you guys how to do that next Wednesday. But anyways, Aviation Weather Center, you guys can basically look up METARs, TAFs. You guys can look up all the different weather products that we're going to basically be talking about today, and kind of poke your nose around. You do not need any type of login or anything like that. And they do also have some international stuff for our students elsewhere. Anytime that you go to any weather product, though, I would encourage you guys, if you're lost and you have no clue what the heck you're looking at, there's an info button in the upper right-hand corner of every single page. And if you want to know more about whatever you are looking at in terms of how often does this weather product come out, what's the purpose of the weather product, how do you decipher this, what's the legend, just click that info button and you'll get further information about exactly whatever page you happen to be looking on. Okay, so use this as a resource. I know a lot of people, you guys will eventually end up using EFBs, so like ForeFlight and Garmin Pilot and FlyQ, they all have different pre-flight briefing packets that do include weather as well. A couple other resources for you. You guys can basically take a look at these textbooks, and these are basically produced by the FAA, so they are completely free. And we do put a copy beneath this live stream as well. I believe in the documents they are PDFs, and these are called AC circulars, advisory circulars. If you want to, and you're more of a physical book person, you can purchase these. Currently, though, I think we're still in change 1 for the aviation weather services, but you guys can usually purchase these as well. You can find them on Amazon or any other flight or bookstore out there if you want the physical copies. The blue book on the right is pretty much everything that we're covering in class today. So this is really all of the basic weather information and beyond. And the reality is that we will cover a very small portion of the blue book that you will need to know for the purposes of a private pilot. As you kind of go up the food chain, basically by the time you guys, if you guys end up going to airline transport pilot, you would have read the entire book. So it's kind of interesting. It's kind of a building format in the sense that you'll learn a little bit more each license or rating that you get. So keep that in mind. If you want to kind of go dive further into the topic and you're a lifetime member, just go check out the aviation weather for the other classes. They're slightly different with more advanced topics. If you're just interested in aviation weather, I would encourage you guys to take a look at the blue book. They even have space weather in there as well, which is a new kind of interesting, forecasting methodology. The white book, on the other hand, is all your aviation weather services. So these are going to talk about the 3 different types of weather information products. So we have observations, analysis, and forecast. It's a huge book. It's over 400 pages. And it's going to provide a lot of information, just like the info button on the last one of what the heck are you looking at? How often does this weather product come out? How do I read this? What's the legend for it? And the list goes on and on. So this is really to be used as an aid, and the reality is that we will only talk about 6 or 7 different weather products in this class. There's closer to over 100 different weather products, and they're basically ever changing. There's even some within the Aviation Weather Services book that you guys see on the screen here that are no longer in use. Okay. All right, let's go ahead and talk about the Earth and what is the major source of all the weather. So you guys can throw this in the chat. What do you think the major source of all the weather is? Okay, but what causes weather here on Earth? Here's some interesting ones out there. Bill, on the website, if you look down beneath here, and I'll ask Travis. Travis, can you just reconfirm for me? And under the weather section, under the documents, can you make sure that Aviation Weather Services PDF and the Aviation Weather PDF is also listed under there? We'll double check it for you guys. Uneven heating of surface, sun, climate, uneven heating and cooling of the Earth, the sun, uneven heating, sun, Jesus, heating of the Earth, moon, Coriolis effect, unequal heating, heat and cold, ocean, tribbles, don't know what that one is. The Great Arc Seizure, uneven heating, temperature, sun, rotation, sun, moon, tacos. All right, so you guys are on the right track. It does actually have to do with the uneven heating of the Earth's surface. So very simply, if we look at the sun is not actually hitting the Earth in its entirety, 24 hours a day. It's only basically capturing or hitting the Earth part of the day, okay? But at the end of the day, the major source of all of our weather is going to be the sun and its changes of our variations of weather patterns that actually are caused by the uneven heating of the Earth's surface by the sun. So the unequal heating of the Earth's surface creates large air cell circulation patterns. And don't be intimidated by this. This is just a fancy way, a cell air circulation is a fancy way of saying wind. Okay, it's like a sciencey way of saying wind. Okay, so now the reason why we have different wind patterns is actually due to either temperature differences, which actually cause wind to develop and then move heat from air from hot temperatures to colder areas. And the variation is caused by a number of things. It's caused by latitude, meaning how high up we are, or either higher closer to the poles, or if we're closer to the equator, topography, and also our altitude as well. Now, the other thing, if you kind of take a more advanced approach to it, is going to be, if anyone here has ever taken a science class or basically an environmental science class, there is the hydrologic cycle, and we're not going to get into that, but the one thing I do want to show you is the table on the left from the FAA. So very simply, every single type of material or substance here on Earth can basically absorb and dissipate heat at different rates. And if you look at the little science experiment that we have here, we're basically lighting a candle. That candle is putting out 4.18 joules of heat. And we can see here that we've got a gram of water and a gram of sand. And what we're going to do is they start off at the exact same temperature, 25 degrees Celsius. And after that energy has been expelled from the candle, you'll notice that it took a lot of energy just to basically get the gram of water to be 1 degree Celsius warmer. And yet that same amount of energy basically increased the sand from 25 degrees Celsius to 30 degrees Celsius. This is what's known as a specific heat capacity. Okay, so very simply, there's differences in specific heat capacities, and this is one of the primary reasons why temperature of a body of water, such as a lake or ocean, is going to be less variable with time than the surface of land or basically anything with on land. If you're anywhere in the Southwest on a very hot day, if you guys basically wait till the sun goes down and it's kind of dusk, you can still stand next to a building and you're going to feel that radiant heat coming off of the concrete or whatever type of material that is, well past when that sun is actually below the horizon. And yet, that's the reason why our oceans really do not, on a very hot day, the oceans don't go from 60 degrees to 90 degrees and then at night cool down. So every single material on Earth has different, it can basically absorb heat and dissipate heat at different rates, which is kind of also a more appropriate or interesting way to kind of think about it when we're talking about beyond the unequal heating of the Earth's surface. So going back to our single cell air circulation, if the Earth was not rotating, this would be basically what that single cell wind pattern would look like. Very simply, we've got the warmer air at the equator, which would rise, and then it would basically continue moving upwards to the pole, North Pole in our case, and then it would descend as it gets cooler, and then it's basically a rinse and repeat pattern. Now, of course, this is not necessarily the case because, as someone said, we do have the Coriolis force, and the Earth actually does rotate. And the Earth is going to rotate counterclockwise if we basically looked at it from an above position. If anyone here has an LP disc of any type, and if you were to put tissue paper over an LP disc and actually plate it, and you attempted to basically draw a straight line, what you'd realize is it's actually going to, that straight edge is going to start to curve, okay? And because the Earth rotates, this large simple cell, the simple cell air circulation pattern or this wind pattern is going to be greatly distorted due to the Coriolis force. And keep in mind, everything in our class, because we're dealing with the US FAA, is going to be dealing with the Northern Hemisphere. So you might have to adjust this thinking depending on where you're located elsewhere around the world. But here in the United States, this is the way it basically distorts. So instead of kind of just moving straight up, they actually start to kind of move at right angles. So basically what we have here is our simple wind pattern due to Coriolis force. When the wind first begins to move at the higher altitudes, the Coriolis force is going to deflect it to the right within the Northern Hemisphere. And this is actually going to cause the flow of that wind to move within what we call isobars, or those are basically lines of equal pressure. And we'll talk more about those coming up. At the end of the day, the Earth is always trying to equalize, okay? So high pressure is always trying to move into low pressure to equalize, and that's another part of kind of our more in-depth discussion of weather. Now, the reality is that this is what it truly looks like. Okay, so this is our Northern Hemisphere cell circulation pattern, and we actually have 3 different cells that we talk about. So the first one is closer to the equator, and this is going to be your northwest trade winds. And the northwest trade winds is actually called the Hadley cell. Okay, and the Hadley cell is a low latitude air movement. And what ends up happening is the movement towards the equator. And we have the warmer air. So with heating, it's going to rise vertically with poleward movement in the upper atmosphere. And this is the cell that basically forms the convection that dominates the tropical and subtropical climate. So if anyone here has been on vacation recently or remembers, there's usually a lot more thunderstorms and the winds are moving in a little bit different direction. They're actually moving basically from the east to the west. The prevailing westerlies, which is known as the Ferrel cell, that's what we experience here within the continental United States. And this is the mid-latitude, which actually means the atmospheric circulation cell for the weather. And in this cell, the air flows poleward and eastward near the surface, and effectively the winds are coming from the west and they're moving to the east. Your weather's coming from west to east, which is very common. If you get a little bit higher up, you're going to get your polarly easterlies, which are called your polar cell, and this is as the air rises, it's going to diverge and travel toward the pole. Once over the pole, the air is going to sink, and then it forms the polar highs. At the surface of the poles, the air is going to diverge outward from the polar highs, and then your surface winds in the polar cell are going to be easterly, and that's the reason why we abbreviated the polar easterly. Okay, so you can see, depending on where you are in the world, if you're hailing from Mexico, you're actually going to be within the northeast trade winds. If anyone here has ever been to Cancun or Puerto Vallarta or any of those wonderful places, you'll always notice for the most part, most of those storm systems are moving basically, I want to say from right to left, but it's basically moving from the east to the west versus, out here in the California or basically the Pacific coast, we usually see the weather come off that Pacific Ocean and start to migrate or move further to the east. Okay, so it's a little bit different. All right, let's go ahead and take a look at your very first question. That was a lot of information, trying to give you a bigger picture idea of what to think about. Like I said, some of those topics are a little bit more advanced, but at the end of the day, this is what we want to know. Primary cause of all changes in the Earth's weather is it A, variation of solar energy received by the Earth's regions, B, changes in air pressure over the Earth's surface, or C, movement of the air masses? Yep, so once again, in the United States, we get the prevailing westerlies. All right, we got the first 50% of the class in. What we'll do after this is we are going to take that 10-minute break a few minutes early, and then when we come back, we're going to talk about the structure of the atmosphere and some of these terms, such as relative humidity, dew point, how to calculate the bases of a cloud. We will also talk about, I see a little bit of a discussion right now, what is standard pressure? Should we be using millibars or hectopascals or inches of mercury? We'll talk about when do we use each one of those, and then we'll start getting into the temperature inversions as well. Okay, we got about 80% of the class. About 90%. Just waiting on a few stragglers here. I see that one question. I'm trying to look that up real quick. Someone's asking, do I need to know millibars for the purposes of your private pilot? You just double check to make sure I give you guys the right answer. And the answer is no. Okay. So for the purposes of your private pilot exam or your sport pilot exam, you're not required to know millibars. You will be required to know millibars in the event you go up the food chain to the commercial pilot or your ATP. That's when they're going to start asking you those questions. All right, let's go ahead and take a look at it. We've got 71% of the class with A, 13% with B, and 15% with C. So hopefully you'll see this question in a couple different variations. So the correct answer is going to be A, which is the variations of solar energy received by the Earth's regions, which is another fancy way of basically saying the unequal heating of the Earth's surface. That's another potential answer. Or I've even seen this question with this one, which just says sun. Okay. So if any one of these comes up, if it says, what's the primary cause? Sun would be appropriate. Variation of solar energy received by the Earth's regions would be appropriate. And there's a third one that I've seen, which is the unequal heating of the Earth's surface. That would also, they're all kind of in line with whatever the primary cause is. Okay. Good job, everybody. All right. So with that, let's go ahead and take that 10-minute break. Go ahead and stretch your legs, refresh yourself so we can get into some more weather theory here. Grab whatever your beverage of choice is, recaffeinate, retionate, rebaronate, rebourbonate for those that are drinking. And we'll see everybody back in 10. move on with aviation weather theory here. So the next thing we're going to look at is the structure of the atmosphere. And the two primary structures that we're going to look at are going to be the troposphere and the stratosphere. And the troposphere is going to be based off of just some standard numbers. And what I'm going to put here is this yellow line that you guys see kind of crisscrossing back and forth. This is the change of temperature, basically with the increase of height or altitude. And we will talk about standard temperatures, but one of the ones that I'll throw out right now is 15 degrees Celsius at sea level. That is our standard temperature that we will basically use for a lot of different performance calculations and what manufacturers and testing and scientists use. But very simply, the troposphere begins on the surface of the Earth, and then it can extend up to 36,000 feet high. And the temperature within the troposphere is also going to decrease with height or altitude. So very simply, at the base or sea level of the troposphere, it is 15 degrees Celsius, which is the equivalent of 59 degrees Fahrenheit. And then as we move up in altitude, the coldest portion is going to be reached at the top of the troposphere, which is negative 56.5 degrees Celsius, or the equivalent of negative 70 degrees Fahrenheit. Now, almost all of our weather occurs, almost about 90% of the weather here on Earth is going to occur within the troposphere. As general aviation pilots, this is the part of the atmosphere that we will be flying in. There are some high-end jets and those types of things that do have the ability to get within the stratosphere, just depends. So once you get to each one of these layers here, you're going to see basically a pause, right? We have the troposphere, and then we've got the tropopause, the stratosphere, and then the stratopause. What basically defines the tropopause is it's basically the boundary layer between the troposphere and the stratosphere, and there's really going to be no temperature increase or decrease within that layer. Now, the other thing that I'll point out is just look at the depth, right? So this depth is fairly shallow compared to the depth of the stratosphere. Okay, the stratosphere is far it's far deeper or higher. I'm just trying to think of the best way to say that, than the troposphere itself. The next layer above it is called the stratosphere. And the stratosphere is going to start at the tropopause and extend up to 31 miles above the Earth's surface. There's very, very little, atmospheric, like water vapor and those types of things. So that's the reason why the weather is really kept to a minimum. But the thing that you want to kind of keep in mind here is that as the temperature increases with altitude, you're going to have radiation, and then because of that, the radiation is going to be increasingly absorbed by the oxygen molecules, which actually lead to the formation of the ozone, and actually starts to warm up the temperature within the stratosphere. You're going to see that yellow line start to kind of reverse itself, and as you climb in the stratosphere, remember at the bottom here, it's negative 56.6 degrees Celsius. And as we start to climb up in the stratosphere, it actually starts to get warmer until we reach the warmest part, which is 3 degrees Celsius or 27 degrees Fahrenheit. Now, the reality is that because it is getting warmer within the stratosphere, but just keep in mind that think of that depth again, right? If we can think about it in terms of, the troposphere is 36,000 feet high, and yet the stratosphere is closer to, almost 20 miles deep. And the temperature difference within the troposphere from 15 degrees Celsius to negative 56 is actually quite dramatic. If we look at it from the base of the stratosphere to the top of the stratosphere, negative 56.6 degrees Celsius to negative 3, it does get warmer, but the changes of temperature are much, much smaller every 1,000 feet compared to within the troposphere. Okay. All right. So let's go ahead and look at another FAA test question. So kind of put on your thinking caps. Think about what was the stratosphere and what was the troposphere, and talk about those characteristics. So a characteristic of a stratosphere is it A, an overall decrease of temperature with an increase of altitude? B, a relatively even base altitude of approximately 35,000 feet, or C, relatively small changes in temperature with an increase in altitude? Right, first third of the class is in. Have a good one, patience. Well, Vlad, it seems like a no-brainer. So glad that you got it. You'd be surprised though. All right, let's go ahead and take a look at this one as well. Looks like we've got everybody in. So I've got 21% with A, 12% with B, and 66% with C. So just remember that the troposphere is the base layer, right? That's pretty much where you guys are flying. The stratosphere is that next layer that we were talking about. So sometimes people, you know, they don't really, they think stratosphere is the base layer, and then they basically reverse it. Okay. So when we look at it, within the stratosphere, as I was trying to allude to, that depth of the stratosphere is almost 20 plus miles deep versus, you're talking about 36,000 feet with the actual troposphere. So within the stratosphere, it is basically a characteristic which is defined by relatively small changes in temperature with an increase of altitude. Okay. For anybody that said A, which was the other majority, 21%, A is incorrect because temperature increases. It does not decrease with altitude. If I asked you what a characteristic was of the troposphere, then A would be the correct answer. Okay. And B is incorrect because the stratosphere fluctuates in altitude. So basically, as the base is higher at the equator compared to the poles, it's not always going to be 36,000 feet. It could be higher and it could be lower, just depending on where you're currently located. All right, good job, everyone. Now we're going to get into some more of these terms. Relative humidity, also abbreviated as RH. This is not something we really use in aviation. We're going to use a term called dew point, but they're going to have basically the same meanings here. So keep in mind, any parcel of air is going to hold some amount of water vapor in it, okay? And when you look at this, what we've got is the amount of water vapor present can be expressed by either relative humidity or a dew point. And you'll see that in aviation, we primarily use the term dew point. Temperature is largely going to be determines the maximum amount of water vapor air can hold, and warm air can actually hold more water vapor than cold air. And the way that we get to the RH value, or the relative humidity, is we just take the water vapor content and we divide it by the water vapor capacity. Okay. So the relative humidity is just the ratio, usually expressed as a percentage of water vapor actually in the parcel of air compared to the amount of water vapor the air parcel could hold at a particular temperature and pressure. So that is what relative humidity is. Now, what we're going to use is we use the term dew point in aviation. And dew point is the temperature to which a parcel of air must be cooled to become 100% saturated. Now, dew point, the reason why we use dew point is a great indicator of atmosphere's water content. So higher dew points are going to indicate a higher moisture content. And just like you guys heard on all of the ATIS informations that we listened to over the telephone recordings, and also the ASOS and AWOS, they always provide us the temperature and dew point value, right? Usually said temperature 11, dew point 15, altimeter, something. And that's known as the temperature dew point spread. And that refers to the actual temperature difference between the temperature and the actual dew point. Anytime that you see something like temperature 11, dew point 12, right? That means that if it is within 6 degrees of each other, and in that case, that's less than 6 degrees, there's going to be a high potential for either fog or low-level clouds to form if the temperature dew point spread is within that 6 degree Fahrenheit. That's going to be Fahrenheit. Now, they're always going to be reported in Celsius, so that's where you might have to kind of think about a conversion. There's going to be no conversion questions that's going to ask you anything about dew point, but just realize that the closer that those two numbers are together, if I said that the temperature was, I don't know, 21 and the dew point was 15 or something like that, or even if I were to give you potentially, let's say it's just cold, let's say the temperature is 5 and the dew point is 30, If the numbers are very, very far apart from each other, then it's going to be more likely that you're not going to have any type of fog or low-level clouds. Okay. All right, so let's go back to your definitions here and figure out which is the most appropriate definition. Let me go ahead and open up the test question. To which meteorological condition does the term dew point refer? Is it A, the temperature to which air must be cooled to become saturated, B, the temperature at which condensation and evaporation are equal, or C, the temperature at which dew will always form? Julie, it does not matter which it is, as long as they're within 6 degrees Fahrenheit of each other. All right, got the first 40% in. About 80% now. All right, let's go ahead and take a look at this. We get about 80, almost 89% with a couple people on B and C. Majority of the class has the correct answer here. So remember that definition. It's going to be the temperature to which air must be cooled to become saturated. Okay. And if you want to think about it, this is something that we're always really going to look at. So when you look at that temperature dew point spread, just remember, if you see numbers that are very close together, it is more likely in those situations that you're going to have fog or low-level clouds, or even potentially rain, in the near future. Okay. All right. The next thing we're going to look at is how to calculate the base of a cloud. And with this, the one thing I need you guys to write down is this formula. Commit that to memory. You will have a couple FAA test questions. There's actually two that are potential on the FAA exam, and everything else on that page you can disregard. But for some of us, or for some out there, they're always asking, well, what is the temperature lapse rate and all this other stuff? There are, I want to say 3 or 4 temperature lapse rates. Don't worry yourself too much about them in this class, but the reason why I put this one in the bullet point at the top is it's what's called the actual temperature lapse rate of a rising parcel of non-saturated air is 5.4 degrees Fahrenheit per 1,000 feet. And that basically correlates to the formula at the bottom. That's basically the information that they're using to determine the base of the cumulus clouds. The reality is just remember, this is never, ever going to be asked until you get to a higher level, such as commercial or even your ATP level. But what we do is we use that information above, and we're able to actually estimate the temperature and the dew point will come close enough together to form the bases of clouds. So it's very simply, what we're going to do is we take the temperature and we subtract that value from the dew point, and that should actually be written a little bit differently. And we're going to divide that by 4.4, and then we're going to multiply that number by 1,000. Okay, and that's going to tell us the height in thousands of feet in terms of what those bases are. Okay, so temperature minus dew point divided by 4.4 degrees times 1,000. Yeah, and for those that, and once again, if you read that blue book, you can learn all about the temperature lapse rate. We're only going to talk about one in this class, but I think there, like I said, there's like 3 or 4, if memory serves me correctly. All right, so let's go ahead and take a look at the next FAA test question. So I'm hoping everyone wrote down that formula, hint, hint, if we can put it into practice here. All right, so breaking out your calculators, using the information as follows. So at approximately what altitude above the surface would the pilot expect the base of cumuliform clouds if the surface air temperature is 82 degrees Fahrenheit and the dew point is 38 degrees Fahrenheit. Would we expect them at 9,000, 10,000, or 11,000 feet AGL? All right, got the first 40% of the class in. Yeah, unfortunately, you're going to see things in Fahrenheit and Celsius on the exam. I know it's kind of a pain in the keister there. The reality is that once you get into like the more practical day-to-day flying, you're really only going to be dealing with Celsius. And the cool thing is if you guys have an E6B, it's very easy to calculate the difference between Fahrenheit and Celsius, or vice versa. All right, we're about 70% in. Right, about 90%. You do not have to convert anything based upon the formula I gave in the previous slide. The previous slide, that value at the bottom of the equation is based off of Fahrenheit. All right, let's go ahead and take a look at it. I'll leave it open for any last minute stragglers here, but very simply, we just want to know what the base of these clouds are, and we need a couple pieces of information. We do have a value of 82 degrees for the air temperature, and our dew point is 38. So very simply building that equation, we basically have the 82 degrees Fahrenheit. We're going to subtract that from 38 degrees Fahrenheit, and we're going to divide that by 4.4 degrees Fahrenheit. Okay, so simple math, 82 minus 38 would give us 44 divided by 4.4, which would be, think about a 10, okay? And then what you're going to do is you're going to take this value and you're going to multiply 10 times 1,000, which will then give us 10,000 feet AGL, and the correct answer would be B. We had about 91% of the class get that, so pretty simple. I think the hardest thing about this question is really just kind of remembering or memorizing that formula. The reality is once you guys get past the written exam, you can basically dump that information. You do not need that for really anything other than that. No one's ever going to ask you that on a check ride. All right, let's go ahead and talk about standard pressure here. So as I said before, there's a number of different units for atmospheric pressure. And atmospheric pressure is basically anytime that we have the atoms and molecules that make up the different layers of the atmosphere, they're always moving in random directions, up or down. So when they do so, even though that we can't see them, they're actually striking either each other or a surface object. And when that basically occurs, they're going to exert some type of pressure. And the pressure, it's that pressure or that force per unit area exerted by the weight of the atmosphere. And we use different units of pressure, as you guys can see on the right. Now, the two that I highlighted in red are the most common ones that we use, millibars and then inches of mercury. You guys as private pilots will pretty much exclusively be using inches of mercury, or HG. And the standard atmospheric value that we use is 29.92 inches of mercury, okay? The millibars, or MBs, is something that we use in U.S. weather charts. A lot of them, they're going to be for winds aloft. And, 1013.2 is the equivalent of sea level on a standard day. And the reality is as you go up in the atmosphere and as that number becomes smaller and smaller, that just means that the pressure is less, and that means that you're at a higher altitude. If you end up, as I said before, and go to a commercial pilot level or an ATP level, you'll need to know a little bit more about millibars. Another one for the international students, or maybe if you're hailing out of Canada, you guys use hectopascals, which is HPA, and this is the same value as the millibars. It's 1013.2. Occasionally you'll see these on your METARs, which is basically your current weather information. And then for any engineers out there, you guys use PSI, which is 14.7 at sea level. Here's that example. So anytime that you're using some of the charts that use millibars, you can kind of see the corresponding values. So that 1013 is very close to sea level or at sea level on a standard day. And as you can see, as you move up in the atmosphere, you can see that 200 millibars is the equivalent of 39,000 feet. If you have 400 millibars, it's the equivalent of 24,000 feet. There are some charts out there that you could actually search your winds aloft information by looking at they're called millibar charts. So if I pulled up the 200 millibar chart, you'd have to realize that I am actually looking at high altitude, weather, such as right around 39,000 feet. So the way that this works is as we move upwards, or basically climb in the atmosphere, the weight of the air above us is actually going to decrease. And then if we actually held a barometer with us or carried it, we could actually measure that decrease as the weight of the air is actually decreasing as well. So all standard altitudes are based on standard temperatures, and in the reality or real world here, they're rarely going to be standard. Okay, so our standard temperature is going to be 15 degrees Celsius, right, that I said before, and our standard pressure is 29.92 inches of mercury. The reality is that every day you wake up, it's never going to be 15 degrees Celsius, which is the equivalent of 59 degrees Fahrenheit. It's never ever happens to be standard. So we have something known as a standard temperature lapse rate. And remember, commit these numbers to memory here. Remember, standard temperature at sea level is 15 degrees Celsius, and we're only going to deal with Celsius. I threw in the Fahrenheit if you want kind of a comparable number, the equivalent of approximately 59 degrees Fahrenheit. Our standard lapse rate is 2 degrees Celsius per 1,000 feet. So effectively what we're saying is that as we climb up in the atmosphere, every 1,000 feet that we gain of altitude, it should get 2 degrees colder. Okay, should get 2 degrees colder. So very simply, if you wanted to know what is the temperature, let's say we want to know the temperature at 10,000 feet. Okay, we could try to basically figure that number out based upon the standard lapse rate. Okay, so let's assume we have a standard day. So over here at sea level, it is now 15 degrees Celsius. And we know that every 1,000 feet, it gets 2 degrees colder. So what I'm going to do is figure out how many 1,000 feet that we're going up. And in this case, we're going up 10 of those. Okay. So if I was to take 10 and multiply that by 2 degrees, okay, that means that it should theoretically be 20 degrees colder than it is at sea level. So the temperature, if everything works out appropriately at 10,000 feet, it should be roughly about -5 degrees Celsius. Okay. And we can use that standard lapse rate, and we use that for a lot of different things. We're going to use that for performance information. We're going to use that to, try to figure out where the freezing level is. We do that quite a bit for instrument flying. So just because we have the ability as instrument pilots to fly through the clouds, we don't want to fly through the clouds and accumulate a lot of ice because we don't have a lot of, preventative measures to help us out. Okay, we don't want to turn into a giant ice cube. So a lot of times for instrument pilots, we'll use this information to try to figure out, okay, what's the temperature on the ground? It's 30 degrees Celsius, and I want to climb up to 10,000 feet. So that's going to be 20 degrees colder. So it should be 10 degrees Celsius. Is that, am I within the freezing range or not? Okay, so that's what we mean by the standard temperature lapse rate. So all things being normal, as we climb up in the atmosphere, it should get 2 degrees Celsius colder every 1,000 feet that we climb up. Now, of course, as I've said before, that would be in a perfect world. A lot of times what we have is we have these things called a temperature inversion. Okay, temperature inversion. A temperature inversion is just basically the opposite of standard. So instead of getting colder as we climb up in the atmosphere. In this case, it's an inversion. It basically is getting warmer, okay? So there's two different types of temperature inversions. There's one known as a surface-based inversion, and then there's an aloft-based temperature inversion. The surface-based temperature inversion is going to most often develop near the ground on clear, cool nights when the wind is light. So kind of think about it like this with the desert. And you've got, as soon as the sun goes down, you basically have this warm parcel of air sitting right here, and the ground is actually going to cool much, much faster than that parcel of air. So the ground is going to radiate and cool much faster than the overlying air, and then air in contact with the ground becomes cold, while the temperature a few hundred feet above is going to change very little. And that's actually what causes that temperature to increase as we gain altitude. So very simply, what ends up happening is if you take off, what you'll see is that this white line is representing the temperature. Okay, so right here, it is actually starting to get warmer. And then once you get past that inversion, everything will normalize and it will start to cool off at 2 degrees per 1,000 feet. Okay, so it's kind of just this warm parcel of air that's kind of stuck very, very close to the ground. So this is one type of inversion, and that's the reason why we call it a surface-based inversion. The next type of inversion we've got is called an aloft-based inversion. So it's basically the same concept, except that warm parcel of air is going to be a little bit higher up in the atmosphere. It really depends on the day. I've seen temperature inversions where these parcels of air sit at 1,000 feet, or they could sit at 3,000 feet. It just depends. So if we're flying or we take off from the St. Louis airport here, as we climb up, we'll notice that it is actually starting to get colder. Okay, so as we climb up in the atmosphere, we are getting colder. It is based upon the standard temperature lapse rate. We are getting 2 degrees colder every 1,000 feet. But eventually, we're going to basically hit this warm parcel of air. And once we get in it, what will end up happening is the temperatures are going to reverse the trend, and it'll actually start to increase. Okay, it'll actually start to increase. Eventually, as we get towards the top of that inversion aloft layer, the temperatures will start to revert, and as we start to climb in altitude, it will once again start to decrease within what we're typically used to. Okay. Couple ways that we can see signs of inversions, especially at higher altitudes. If you're flying in the flight levels, usually above 18,000 feet, you can usually look at the top of clouds, and they start to create this like pancake-like shape, and they start to flatten out. That's a pretty good indication that there's an inversion of loft. There is no altitude limit on these things. They could be really at any altitude. And as pilots, a lot of times as a general aviation pilot, in a cockpit that doesn't necessarily have heating or cooling capabilities, in the LA area, if you take off, and it starts to get really, really warm as you're climbing, that's usually that's going to be your first clue that you're going to have an inversion aloft there. All right, other visual signs would be basically any type of smoke or really anything, any type of pollutant, smoke, or anything else will get trapped in the inversion. It does create that lid that creates that pancake-like flattening that you're kind of seeing there. So that's a really good sign. So here we've got basically a wildfire or some type of smoke in the distance, and it is basically being held in with that temperature inversion that's kind of holding a lid on top of it. The same thing, if you have stratus clouds, which are these nice poofy clouds, this is all going to be based upon a surface inversion. There's basically a lid on top of this, basically not allowing any type of vertical development. And it's really holding it down. Another way to basically determine a inversion aloft. As I said, if you are flying below an inversion, you're going to usually see a lot more pollutants. Expect just lower visibility or poorer visibility because of a temperature inversion. All of that stuff, the pollutants, the smog, anything else will be basically trapped in there. And then once you climb out of that inversion layer, you should be able to get a lot better visibility. Now, the reason why we're talking about inversions is not just because it gets hot, but primarily because of this thing called wind shear. And wind shear is very common within a temperature inversion. And it's basically going to occur where the cold air and that warmer parcel of air are meeting, and they basically don't like to necessarily mix. So let's start off with what the heck wind shear is. So wind shear is basically a sudden change of direction and or velocity. Okay, a sudden change of direction and or velocity. And it could happen vertically or it could happen horizontally. So we can see this example of wind shear here, where in the cooler parcel of air, the wind is going 3 knots, and I'm just going to say, for simplicity's sake, from the east to the west. And in the warmer parcel of air, it's completely shifted direction and speed. Okay, it's moving at 25 knots from the west to the east in this case. Okay, that would be wind shear. Now, wind shear happens in the atmosphere at all altitudes. Honestly, it is not really that significant for you guys until you guys are coming into land or take off. So we have something called low-level wind shear, or the way you're going to see that abbreviated is LLWS, which is low-level wind shear, which is wind shear that occurs at 1,000 feet AGL or less. And anytime you have low-level wind shear, that's going to be more significant because as you're coming in to take off or land, this is when you kind of have to be a little bit more alert, because if you start to lose airspeed, obviously you're very close to the ground. This is actually not as much of the problem. It's still a problem for general aviation pilots, but if you are flying a piston aircraft, the piston aircraft are very, very responsive. So in the event you start to see your airspeed decay or start to bleed off or get lower, you can just immediately apply power to kind of balance that out. This is actually more serious in the airline industry because of the fact that they fly turbine-powered aircraft, and there's something known as spool-up time. So when you're flying a turbine-powered aircraft, if we start to lose airspeed very, very quickly on an approach and we're close to the ground, just because the pilot adds full throttle and it's a jet engine does not mean that jet engine is going to react immediately. There's something called spool-up time, and it can take a few seconds for it to generate enough energy to get you at a faster speed compared to a general aviation piston-powered airplane. So a lot of times, if you are experiencing low-level wind shear, and you'll learn this with your flight training, you're actually going to use a faster approach speed on landing and also use a little faster speed on your rotation and departure. So that way, should you lose any type of airspeed while you're close to the ground, you're still going to have enough energy to basically not allow you to stall. Okay. So within this parcel of air, we can see that there's something called a shear zone, where basically this warm air and this cold air do not necessarily want to mix, and the shear is what's going to cause that turbulence. The other factor here is because we have different wind speeds and also the directions completely change, right? That's also going to cause wind shear as well. So looking at that with an airspeed indicator, in this example, it's not as extreme. In the colder parcel of air, we basically have, I'm going to say west and east again here. We have wind coming from the east, and it's at 15 knots in the colder parcel of air. And as the pilot takes off, they're starting to climb up, and you'll notice that their indicated airspeed is 100 knots. As they start to go through the shear zone, they will see oscillations of plus or minus. That's fairly common. And if you're at a faster airspeed, it's not as significant of an issue. Okay, so even if the pilot loses some airspeed, they're still pretty far away from a stall at that point, right? Now, as they get into the warmer parcel of air, the airspeed will stabilize, assuming that they haven't adjusted really anything in terms of their nose-up attitude or their power setting. It'll basically stay at 100 knots, even if they're continuing to climb. And you'll notice that in the cooler parcel of air, that was a tailwind, right? That's basically a tailwind, and then it basically shifted to a headwind, and that headwind shifted 25 knots. Once they're coming back down and they're coming into land, they're basically at an approach speed of 90 knots indicated. As they get through that shear zone, what you're seeing here is some more oscillations, and when you're at a slower airspeed, this is the reason why it becomes more serious. It's also more serious if you go from, if you have wind shear that basically shears from a headwind to a tailwind here, because you're losing a lot of airspeed. And you can see at this position, you're very close to a stall, and that's obviously not good, okay? If the pilot does not make any type of corrections and basically continue descending and it would basically bounce along, it should, with the same power setting, result in 90 knots indicated once they're fully within that cooler parcel of air. Okay. All right, let's go ahead and look at the stability of the temperature inversion here. So very simply, we all know that hot air rises and cool air likes to stay closer to the ground. So in those types of situations, that is going to be considered basically a stable air mass. And if we look at the stability vice versa with the cold air on top and the warm air on the bottom, that's actually going to be considered unstable air because it's going to want to mix, and the warm air is going to want to move to the top and the cold air is going to want to move to the bottom. Okay, so anytime that we have these types of situations, just remember what we're looking at with the warm air on top and the cool air on the bottom. That is going to be a stable version of a temperature inversion versus what we see on the right hand side as shown. Okay. All right. Let's go ahead and look at a few FAA test questions. Then we're going to move on to the atmosphere and clouds. Let's go ahead and open this one up real quick. A common type of ground or surface-based temperature inversion is that which is produced by, is it A, warm air being lifted rapidly aloft in the vicinity of mountainous terrain, B, the movement of colder air over warm air, or the movement of warm air under cold air, or C, ground radiation on clear, cool nights when the wind is light? All right, got about 40% of the class in. Termaine, just remind me to go back about the -5 that you were seeing. That's just a calculation, by the way. So that was, we're trying to assume at 10,000 feet what would be the approximate temperature. But I can go over that at the end of class here. I have the wrong question up. Let me see. Weather conditions, thank you very much. I think I entered those incorrectly. That's the right question there. Which weather conditions should be expected? Thanks again. All right, give you guys a couple extra seconds, but I know we've got more than about 70% of the class in. Sorry for throwing up the wrong question there. Well, Keith, if it still varies from your cell to your laptop, that's probably because you're watching on two different feeds, and some of the feeds are a little bit delayed if you're watching elsewhere. All right, let's just go through these real quick. So let me go ahead and pause it there. I'm going to go ahead and close out the poll for whichever one that was. And I think I see exactly what happened. So what you have is you basically have these answers, A, B, and C, with this test question, and I kind of reversed it there. So I think I had fat fingers and was probably trying to multitask in a bad way. So sorry, everybody. Let's go through these two. And for anybody that answered, you can disregard that. So a common type of ground or surface-based temperature inversion is one that is produced by, and in this case, this is that surface-based temperature inversion. Remember, just kind of think of the desert. It's going to be most likely by ground radiation on clear, cool nights when the wind is light. Okay? When the wind is light. All right, let's go ahead and look at that other one. So like I said, I think I took the answers and just swapped the test questions. So here is the other test question I wanted to ask you guys. Which weather conditions should be expected beneath a low-level temperature inversion layer when the relative humidity is high? Okay, relative humidity is high. And when we look at these, the best answer here is actually going to be A, and it's going to be smooth air and poor visibility due to fog, haze, or low clouds. The reason why it's fog, haze, or low clouds is the relative humidity is going to be high, right? The higher the humidity, the more likely that we're going to have those low clouds or fog to potentially actually form. So remember that if we looked at, I know some people would probably say B or C. B is actually going to be incorrect because wind shear may be expected within, but it's not going to be beneath a low level temperature inversion. So that's the reason why B is incorrect. And C is also incorrect because an inversion causes steady precipitation and it actually creates a stable layer of air. And it's actually going to be a stable layer of air is just saying another way of basically saying smooth or not turbulent conditions. Okay. So that is the correct answer. A should have been there. Sorry for throwing up the wrong. You guys can completely disregard what's in the poll. Sorry about that. So don't confuse yourself with the poll. Just kind of look at these test questions as they're on the screen right now. All right, let's see if we can do the poll again. I wish I have to keep pushing on. I can't do the poll after I give you guys the answer. That's not fair. All right. So let's talk about, let's see, any other questions real quick. We'll talk about, so let me see if there's any other questions on that very last one. The inversion layer is like a lid. Yep, exactly, Lori. And very simply, it traps in all those pollutants, right? So when it does that, we get that nice smooth air, right? And that's really, if you go back to the original slide where we looked at this, the smooth air is all of this cold air right here. Okay, so that temperature inversion, all that red is going to trap in all of the pollutants from the houses or whatever else they're creating here. And in the cooler parcel of air, not only is all that stuff being trapped in, but the air is going to be relatively smooth and not turbulent within that cool parcel of air. Okay, so that's the reason why it's smoother. The reason why we've got the, back to it, the reason why we have the last part of it, which basically says, you know, fog, haze, or low clouds, is because the test question is telling us that the relative humidity is high. And when we have higher relative humidity, the more likely that we are to have either fog, haze, or low clouds. You don't like the weather section? Okay. Test questions aren't too hard. There are a lot of them, so see if I can get you guys back on track here. All right, so the next thing we're going to look at, and I would write down all 8 of these, is the difference between stability or stable air and instability or unstable air. And these are the 4 characteristics that the FAA wants you to know, okay? So before you get into it, I'll let you guys write these down or take a screenshot of it. The first thing I want to talk about is what the heck is stability? And stability is just really defined as the resistance of the atmosphere to basically develop vertically or have any vertical motion. So what you're seeing on the left-hand side is you have these nice clouds, stratiform clouds, and these are going to be considered a stable atmosphere. And the reason why is that it does not allow any type of stability or atmospheric stability is going to resist any type of upward or downward movement. So very simply, these are just kind of like flat sheets of pancakes. If you look at the instability in an atmosphere, this is going to allow either upward or downward disturbances to basically grow. And right here, this cloud that you can see on the right-hand side is called a cumulonimbus cloud, which is basically a thunderstorm. And this is clearly allowed to grow either vertically up or down. And that is what we're going to consider unstable air. So the characteristics of stable air are as follows. Keep in mind, these are just generalizations, but there is 8 different test questions. So just make sure what you'll see in the test questions are what is a characteristic of stable air or what is a characteristic of unstable air. And of course, they'll give you two incorrect answers and 1 correct answer. So the characteristics of stable air are stratiform clouds and fog, then continuous precipitation, smooth air, which means that there's no turbulence, and fair to poor visibility in haze and smoke. Unstable air has the characteristics of cumuliform clouds, these nice poofy clouds, kind of look like giant cotton balls. Showery precipitation, so it's not continuous, but it's on and off. rough air, which is turbulence, and good visibility except in blowing obstruction. A blowing obstruction could be something like a sandstorm or sand or dust. All right, does everybody have those written down so I can move on to the next thing? Flying next to the big poofy clouds, even though they look cute, number one, you're going to get a lot more turbulence, and number two, the cell that we see on the right hand side, which is a cumulonimbus, which is a thunderstorm, nobody flies in those. Airline pilots don't fly in them. They're gonna destroy our airplanes. Okay. All right. Yeah, they look cute. All right, let's look at one of those potential test questions. And I'm double checking. Looks like the poll matches up here. What is a characteristic of stable air? Is it A, stratiform clouds, B, unlimited visibility, or C, cumulus clouds? Now, of course, one of these is going to be correct, and the other two are going to be associated with, obviously, unstable air. Good point. Hurricane hunters, they do. Yeah, I mean, there are certain aircraft that are highly specialized with highly specialized crews that purposely fly into these things, whether it's a hurricane or a thunderstorm or doing research. But for the most part, most of these things for a general aviation plane, let alone a business jet or even an airliner, we don't fly into. It has the potential of causing structural damage to the airplane. All right, got about 60% of the class in. About 80% now. All right, apologize if I cut off anyone. We've got about 91% of the class with A and just a couple of people with B and C here. So majority of the class does have it correct. So remember that because the stable air resists convection, right? Basically that upward or downward movement, the clouds in the stable air are going to form in horizontal sheet-like layers, or what we call strata. Okay, so what we're looking for here is the stratiform clouds. B is actually incorrect because, once again, unlimited visibility and cumulus clouds are going to be characteristics of unstable air. And C is also incorrect because cumulus clouds are going to be a characteristic, once again, of the unstable air. All right, let's look at one more thing before we take a 5-minute break. Just give me an extra couple minutes here. So the next thing we want to talk about is basically the pressure. Essentially, you have high pressure and low pressure systems, and remember that the Earth is always trying to equalize. It's always trying to get from high pressure to low pressure, or basically high pressure will feed into low pressure is another way to think about it. Now, there's different ways that these move, and just go to the next one real quick here. And keep in mind, everything we're talking about is northern hemisphere. So air is going to circulate in a clockwise direction around a high, and it actually moves counterclockwise around a low. And low pressure, and this is important, is that it moves counterclockwise, but it moves up. Okay, high pressure moves clockwise, but it moves down. Okay, so the reason why high pressure is generally associated with good weather is because it's kind of keeping a lid and not allowing any of these clouds to really develop vertically. The low pressure is really encouraging these clouds and cells to develop because it's basically pushing up. So anytime we're looking at this, this is basically convection, and this is caused by either what we call unequal pressure gradients or the uneven heating of the Earth's surface, which also results in uneven pressure. The easy way to remember this, though, is if you were to just take your hands, right? So like this, but obviously from this position. Obviously, my left hand makes an L, okay? So use your thumb and go like this and kind of do a thumbs up. What you're going to see is that the low is going to basically move counterclockwise and up, okay? So just take an L, pick out your thumb, and kind of go like that. And as you can see, as I'm moving that up, that's basically moving counterclockwise and up. So that means that the opposite is true with a high, which moves clockwise and down. Okay, easy way to remember that. What we look at is we do utilize basically different types of weather charts, and what you're going to see when we come back from the break is we're going to look at these things called isobars, and isobars are just lines of equal pressure. These are actually represented in millibars, and the big kind of takeaway is the closer that those lines are together, the stronger the wind speed. Okay, the closer the lines are, the stronger the wind speed. And one thing that does not really, that kind of interferes with how the pressure systems operate is the closer you get to the ground, there's something known as surface friction. So surface friction could come from either man-made or naturally occurring objects within that vicinity. And then the surface winds don't necessarily move exactly parallel to those isobars, but the same rules will apply, okay? So with that, let's go ahead and take a 5-minute break. When we come back, we will look more specifically at these isobars and kind of see which direction they move. And keep in mind, we don't need to know anything about millibars. All it is just pay attention to the picture and which of the lines are closer together and which ones are further apart. The closer that those lines are together, the stronger the wind. The further those are apart, they're not as strong. Simple as that. All right, so go ahead and stretch your legs, and we'll come back in 5 and push forward. Everybody, welcome back from break, and we're pushing on with aviation weather theory. Got a couple more topics here, and then we'll start briefly diving into the practical side. Whatever we don't finish up today, we'll go ahead and finish up on Monday. All right, so as I said before, kind of putting this into perspective here, this is just one example of obviously a high pressure and a low pressure system. The high pressure is obviously shown by the author moving clockwise, and it basically moves clockwise and down, and the low pressure is moving counterclockwise and up. And as you can see, the high pressure is feeding into the low pressure, okay? Now what this would actually look like, depending on what chart we looked at, there's several different charts that have this information. One of the primary charts would be what is known as a surface analysis chart. You guys can throw in the chat though if you know what that is right there. But here are basically the isobars, and those isobars, like I said, are lines of equal pressure. And very simply, they have basically a value associated with them, and then you can see the squiggly lines in kind of all different directions. The further spaced apart they are, the less the winds are not going to be as significant. And keep in mind, the other thing this will also show is the high pressure and the low pressure systems. So remember, high pressure is generally associated with good weather. Low pressure is generally associated with bad weather. And keep in mind, those are generalizations. Occasionally, it's not true. And the other thing that this is also going to show us is the different fronts. And we'll talk about fronts here a little bit later. But that's what all of these blue lines are. There's basically a couple different fronts, whether it's a cold front, a warm front, a stationary front, or an occluded front. We'll get into those in a little bit. The other thing that you'll also see is troughs and ridges. There is a trough here. Basically, it is right here. We can see that it almost looks like an orangish line. That orange dashed line, which should actually be a red dashed line, that is a trough coming off of the coast of Oregon through California. And a trough is just an elongated area of low pressure. The opposite of that would be a ridge, and a ridge is just an elongated area of high pressure. So most of you guys said the correct thing or something similar to it. Tropical storm, tropical depression. Yep, hurricane is what we're looking for there. So if we look at the information panel on the lower left-hand side, we can see the type of chart this is. This is called a surface analysis chart. We see the date it came out, when it was issued, and we even have the analyst's name and the different centers that put out this information. One of them being the National Hurricane Center. As you can think about it this way, lows, the low or the system inside of a hurricane is low pressure. So there is, if we zoomed in, actually a little L somewhere in there. And then of course the tightly configured rings around it are also going to basically equate that speed, right? So the closer that those isobars are together, the more powerful or the stronger the wind is going to be. So very simply, if you're flying pretty much through most of the continental United States, there's not a lot going on. There is something, a low pressure system where the winds are going to be a bit stronger north of Michigan and Canada. We can see that they're starting to come together a little bit more, but it's not going to be anything, you know, like a hurricane. Okay. The line that's running through New Mexico and through Texas, that is, I have to look at the legend on that. You're talking about this thing right there, that little, I want to say that's an occluded front, but I'd have to see how they're representing that. We have basically an occluded front right there, but sometimes they actually use different color codes depending on if it's a occluded front, whether it is based upon a cold situation or a warm situation. So could be the dry line. Is that what it is, Alex? I see the occluded, but that one gets slicing through Texas. That sounds like a dry line. I haven't seen dry lines in a long time, so, but it could very well be true. All right, the next thing we're going to do is we are going to talk about things and clouds, and you'll be kind of amazed in terms of how many different cloud variations exist out there. All right, so let me just talk to you real quick here. I used to just say, prepare to write down everything in this video, and someone, you know, sent me a nasty email back saying, why would you ever do that? We didn't learn anything. When you watch this video, it's about 8 or 9 minutes. It will go through all of the cloud variation and types out there, and you'll be amazed in terms of how many cloud different variations there are. Enjoy the video, but with that, kind of think about and pay attention to the big thunderstorm ones, what we call those. which are called cumulonimbus clouds. Nimbus obviously meaning rain. And what you're also going to realize is that most of these clouds, in the naming of clouds, the convention is really based off of Latin. So as he says in the beginning of the video, as we all watched this hundreds of times, if you know Latin, everything will be easy from this point forward. But the main thing, kind of the main takeaway, is think about the different height or where these clouds live, right? And we basically have low-level clouds. We have middle-level clouds, which are usually going to have the name alto in it, and then we have cirro or cirrus clouds, which are our highest-level clouds in the atmosphere. And then the third variation of that, or the fourth variation, so low, middle, high, and the fourth variation is thunderstorms, and thunderstorms basically consume all levels of the atmosphere from low to high because they can exceed up to 50,000 feet. And those are the ones that we always try to avoid. Those are the cumulonimbus. And we'll be talking about more about that when we come back from the video. And we'll be talking specifically about what are the ingredients for a thunderstorm to form and what is the evolution of a thunderstorm. There's 3 different stages that we're actually going to look at. Okay, so no emails, just enjoy the video, see what you can get out of it, and I'll see everybody back in about 8 minutes.
Clouds. They bring thunder, rain, and darkness wherever they go, and can even cause damage through flooding and blizzards. For these reasons and more, most people have a negative association with clouds, and many of us have forgotten just how important clouds truly are. In our environment, they play the vital role of delivering fresh water from the oceans onto land through rain. Without clouds, most land would be dry and inhospitable, there'd be no drinking water, and agriculture would be impossible. So I think it's about time we learned more about them. In this video, we're learning all things clouds. There are 3 types of clouds: cumulus, stratus, and cirrus. Cumulus clouds are the big white puffy ones. In Latin, cumulo means heap or pile because they kind of look like big piles of fluff. These clouds typically form low to the ground, less than 2,000 meters up in the lower levels of the atmosphere. But since they grow vertically, they can reach much higher altitudes. Then there's stratus clouds. In Latin, strato means layer, and these form flat horizontal cloud sheets with hardly any distinguishable features. When people say it's cloudy out, it's usually because there's a stratus cloud overhead. Stratus clouds also have possibly the greatest impact on the climate because they form wide spreading layers that reflect sunlight away from the surface, effectively cooling the earth. These also form in the lower levels of the atmosphere and can even become fog under the right conditions. Lastly, there's cirrus clouds, which in Latin connotes a wisp of hair, which I think is a pretty good description. These clouds form high in the atmosphere, anywhere from 7,000 to 14,000 meters up. So high in fact that they usually consist of ice crystals instead of water droplets. The high-speed winds of the upper atmosphere blow cirrus clouds faster than most other clouds, and a lot of the time they'll precede storms to come. Knowing these 3 types of clouds, now we can use the words used to describe them. First, there's alto, which basically means tall or high. This is used to describe clouds that originate in the lower atmosphere, but which have gotten pulled into the mid-atmosphere, anywhere from 2,000 to 7,000 meters above the ground. So an alto cumulus cloud is just a cumulus cloud above 2,000 meters, and the same thing with alto stratus. These will always look smaller than regular cumulus or stratus clouds. There are no alto cirrus clouds because cirrus form above the mid-atmosphere already. Then there's cirro, which kind of gets confusing, but hang in there. Basically, it means very high, like double altos, alto, alto. So an alto cumulus cloud that makes it above 7,000 meters into the highest reaches of the atmosphere would be a cirro cumulus cloud. And same for stratus, becoming a cirrostratus. You can tell these aren't regular cirrus clouds because they aren't wispy, just really small. Then there's the exciting one, nimbus, which translates to rain clouds. First, there's cumulonimbus, cumulus clouds that produce rain, which can become tremendous thunderstorms, sometimes large enough to occupy all 3 layers of the atmosphere at once. You also have nimbostratus, which, as you might have guessed, are flat sheets of rain clouds. There's no such thing as a cirronimbus cloud either. Altogether, it looks like this. Cumulus and stratus are down here. Cirrus are all the way up here. Alto cumulus and alto stratus clouds are right here. Cirrocumulus and cirrostratus are right above those. Cumulonimbus are just huge, and nimbostratus are not so much. There are also stratocumulus clouds, which have similarities to both stratus and cumulus clouds, forming a puffy sheet of clouds. Then there's something called a lenticular cloud, which are stationary and tend to look like discs or saucers. These form when something's disturbing airflow, like a mountain, which causes a swirling area called an eddy behind it. When warm, moist air gets trapped in this eddy, the vapor can condense to form a visible cloud. Okay, so now that we know all that, we can start getting into cloud species. This is where things become a bit complicated and a little tedious, but like super fun too, as each described cloud type has its own internal classifications. Starting with cirrus, there's cirrus vibratus, which form long streaks or fibers across the sky. Then we have cirrus uncinus, which means curly hooks because that's what they look like. Honestly, if you know Latin, this is all very easy. After that, there's cirrus spicatus, which are more dense threads of cirrus clouds. Cirrus flockus look like tufts of wool, almost like cirrocumulus, but these are made entirely out of ice. Castellanus means fort, so cirrus castellanus forms towers, and are usually blown off the tops of other clouds. And lastly, there's cirrus intortus, which means twisted or wound, and they more or less look like balls of knotted string. Now for cirrocumulus. First, there's cirrocumulus stratiformis, which yes, is all three types of cloud in one. Order of the words really matters here. This is when there are so many cirrocumulus clouds that they form a sheet over the sky. Then there's cirrocumulus flockus, fluffier tufts of wool, and cirrocumulus castellanus, which are slightly more visible towers. And then we have cirrocumulus lacunosus, which means full of hollows and are perforated with circular holes. For cirrostratus, there are only two species. Cirrostratus vibratus, which again are very similar to cirrus vibratus, but a bit more sheet-like. And then cirrostratus nebulosus, which is a very thin, sometimes imperceivable high-altitude sheet of ice. Sometimes the sun will hit them just at the right angle to make a spectacular shining halo in the sky. Then we have altocumulus. There's altocumulus stratiformis, which are low-lying sheets of puffy clouds. Altocumulus lenticularis, those are the cool stationary ones. Altocumulus castellanus, which are very puffy towers. And altocumulus flockus, which are more little tufts of wool. Altocumulus lacunosus are basically the same as cirrocumulus lacunosus, just a tad closer to the ground, in the mid-atmosphere. We're doing all things clouds, so if this feels like a lot, you better strap in. Next, we have altostratus, some of which are actually pretty cool. First, there's altostratus undulatus, which look like little waves or rows, as undulatus basically means waves. Altostratus duplicatus is just when two layers of altostratus clouds are on top of each other. There aren't any pictures of this because, well, one layer blocks the other. That's how it works. But typically, because there's more than one layer of clouds, they'll block out more light. Altostratus panis are very chaotic and look like they were ripped away from other clouds. Altostratus translucidus are very thin, and if you couldn't tell, is translucent, meaning you can see the sun through them. Then there's altostratus opacus, which are basically the opposite, meaning you cannot see the sun through them. Altostratus radiatus are like vibratus clouds, but all filled in, running parallel to each other towards the horizon. And lastly, we have altostratus mammatus, which are fun. They're like hanging pouches and are named after mammaries. They're also pretty rare. For plain stratus clouds, we have stratus fractus, which are just small sheets fractured from larger mother clouds due to high winds. These change very quickly and don't last very long as a result. Stratus nebulosus is another thin, foggy cloud layer, this time much closer to the ground. Stratus undulatus form low-lying cloud waves. These are quite rare and hard to spot, so don't really worry about them. Next, we have stratocumulus clouds. First is stratocumulus stratiformis, which, if you're counting, is two mentions of stratiform in one name. These are the most common types of cloud cover in the world. They're basically fluffy, flat clouds that split often. Then there's stratocumulus cumulogentis, which are the flat clouds blown off the puffy tops of other cumulus clouds. And we also have stratocumulus castellanus and stratocumulus lenticularis, which are very similar to other forms of castellanus and lenticular clouds. Stratocumulus lacunosus are similar to panis clouds, with many holes perforating the body of the cloud, looking like it's being torn apart. Now we're on to cumulus clouds. First, there's cumulus humilis, which are small cotton ball clouds that are more wide than they are tall. They're often called fair weather clouds and usually occur in groups during the summer. Cumulus mediocris are essentially the same, they're just equally wide as they are tall. And then cumulus congestus are the opposite, taller than they are wide. Lastly, cumulus fractus are the tiny bits of cumulus clouds ripped away from one another by the wind. And I saved the best for last, the cumulonimbus species. First, there's cumulonimbus calvus, which are puffy all over, even on top. This means the water droplets at the top haven't reached temperatures cold enough to freeze into ice crystals. Once this happens, however, the top ice crystals spread out and become fibrous, and the cloud becomes a cumulonimbus capillatus. This is when the cloud begins to take on an anvil shape, roughly. Once this happens for a while, the cloud becomes what's known as a cumulonimbus incus, the final form of a thunderstorm. These can grow to truly massive sizes, and if they become powerful enough, they can form what's known as a supercell, which is basically a miniature hurricane. These are the conditions which create tornadoes, which can be some of the most dangerous natural hazards on the planet. So that's it, right? Well, in 2017, a new type of cloud formation was added to the official list of cloud types. The asperitas cloud type is extremely rare and not entirely understood, but it can be identified by having waving or rolling undersides, similar to the undulatus species, and looks super cool. If you see one of these, count yourself lucky and take a picture. Alright, that's all for classification now, but there are a few phenomena I think are worth mentioning too. Here's some iridescent clouds, which you only get when water droplets in a cloud are a particular size and correct angle to scatter incoming light as color. Then these are what's called morning glory clouds, oddly satisfying rows of clouds so rare that only one place on Earth has the conditions for them to form, here in the Gulf of Carpentaria, Australia. This is what they look like from space, though it's still unknown how exactly they form. These clouds have features called Kelvin-Helmholtz waves, formed when two layers of fluid at different densities slide against each other, shearing away the top and bottom of the layers. Helios clouds form when mother clouds grow too rapidly and usually form around a cumulonimbus right before it starts to rain, but can also form around other cloud types as well. Here's one forming on an ash cloud from the eruption of Sarashev Peak. Okay, I think that's it for now. Let me know if there's anything else you'd like to know about clouds or if I missed anything. Thanks for watching until the end. I hope you enjoyed this video, and if you did, please consider liking and subscribing to the channel, where I'll be making more videos like this.
All right, so remember, the main thing the FAA wants you to know is basically clouds live at 3 different locations: low, middle, and high clouds. And then we've got our cumulonimbus clouds, the biggest and baddest of the clouds. Basically consumes pretty much any altitude for the most part. So going back to your knowledge, imagine if I talk that fast throughout this entire class, we'd probably get done in 6 days instead of 12 days here. Let's take a look at this test question. It's a high cloud is mostly composed of, is it A, ozone, B, condensation nuclei, or C, ice crystals? Just think about how high those clouds, or where those high clouds live. Great, got about 80% of the class in. All right, let's go ahead and take a look at it. So anytime that we are dealing with high clouds, just remember that the high cloud family is called the cirriform, which also includes the cirrus, the cirrocumulus, and the cirrostratus clouds. And they, because of how high up they are mostly comprised of going to be C, ice crystals, which is what we had about 86, almost 87% of the class with that correct answer. Okay, so just because of the altitudes that they live at. All right, pushing forward, we're going to talk about the life of a thunderstorm. These are basically the 3 main phases of a thunderstorm. Before a thunderstorm even begins, there's certain, I guess you'd call them, ingredients that are required in order for this to actually occur. So the first thing is that you have to have some type of sufficient amount of water vapor, some type of source of moisture. You have to have an unstable lapse rate. So remember, a stable lapse rate is 2 degrees Celsius per 1,000 feet. An unstable one would be, something other than that. And then you have to have a lifting force, something that's going to push this system up and allow it to grow vertically. The 3 stages, and we'll go into them in detail, are basically the cumulus stage, the mature stage, and the dissipating stage. And for the most part, most of these systems, they can reach upwards of 50,000 feet. So, most airliners can't get to those altitudes and cross them. So a lot of times they have to navigate through, not through them, but around those cells. And of course, for general aviation, we just want to stay well clear of any of these systems. The recommendation is 25 nautical miles from the FAA. Looking at each one of these in detail here, the first one is basically what is known as the cumulus stage, and this is a stage that consists mostly of updrafts. There's some type of initial force that's basically providing what we call this uplifting force here, and we'll talk about a few different types of uplifting forces. We could have it through orographic lifting, which is a way of just saying via a mountain. It could be from a front, like one front taking over another front, or it could be via convection, or it could even be a trough. A trough, remember, is an elongated area of low pressure, and as we talked about before, lows basically go push things upward. As that occurs, you're going to have the moisture, or that moist air that's drawn in, and then in that process, as that system starts to expand vertically, you're going to have all of this heat that's going to start to be released, and that's going to create additional lifting, and that's also going to cause updrafts. The big thing you want to kind of keep in mind is that this stage is going to be mostly updrafts, and what we mean by updrafts is 3,000 feet per minute or greater, so pretty significant. The mature stage is going to officially begin basically at what we call the first sign of rain or precipitation, and that's basically when the precipitation hits the earth. Now this stage is going to be predominantly with updrafts and downdrafts, and this is really where the cell in the system is going to really start to expand, or have already expanded well past and above the freezing level, somewhere into the flight levels. So traditionally what you're going to have, anything below the freezing level, you'll have additional rain and moisture due to those downdrafts, and then really anything above that freezing level, you're going to have ice crystals and potentially even hail that will form and be thrown from the thunderstorm itself. The final stage is basically what we call a dissipating stage, and this is really consists entirely of downdrafts, and this is where the gust front is going to come from. And in certain situations, it can actually cause a roll cloud as well ahead of the storm. A roll cloud is pretty much just a cloud that kind of looks like, like it's tumbling or rolling, and it will usually be ahead of whatever that cell is. In this stage, you're also most likely to see the classic anvil shape. So this is the anvil right here, and the point of that anvil is really giving you that wind direction as well. So remember that even though that there is no cell right here, do not fly anywhere underneath the anvil. Stay well clear. There is hail and stuff that does like to depart from that cell in that general direction as well. And then a lot of times if you pull up weather reports, you can find out the actual movement of the cell in terms of what is the direction it's heading and also the velocity that the cell is heading. And a lot of times they're actually measuring the very top portion of whatever that system is. Okay. So that is your 3 stages of a thunderstorm. You will be expected to know those, by the way. Really the big thing, like I said, is that if I go back to the original slide here, the big kind of takeaway, if you will, is that the ingredients, right? 3 ingredients are needed: sufficient water vapor, an unstable lapse rate, and then some type of lifting force. And then we have 3 different stages. The cumulus stage is entirely updrafts. The mature stage begins at the first sign of precipitation hitting the ground, and it does consist of updrafts and downdrafts. And then finally, the dissipating stage is pretty much entirely downdrafts. So that's really what you need to know there. Those lifting forces, here's a couple examples. So if you have a trough, which is that elongated area of low pressure, remember, troughs want to basically move upward. So in those types of circumstances, that is that uplifting force that the system needs in order to grow vertically. Another one, and the reason why we see a lot of thunderstorms along mountain ridges and in mountainous terrain, is something called orographic lifting, or what we call over a mountain or due to a mountain. Very simply, you basically have some type of air or wind that's hitting it on the windward side, and as that air is basically deflected off that mountain, it will actually deflect it upwards, which will also provide that lifting force for that thunderstorm to basically develop. Okay, these are just a couple examples. You could also have a frontal thunderstorm. A frontal thunderstorm is basically really the uplifting force is a front that's pushing it, and it's usually could occur also when you have one front overtaking another front, which is very common. Basically like a cold front overtaking a warm front is a good example. But the frontal thunderstorms are really pushed via a front. So here we can see a cold front, and cold fronts we're gonna look at the steepness of a cold front versus a warm front, but cold fronts are far steeper in the sense of this right here. Warm fronts are a bit more gradual, and because of that, cold fronts generally, for the most part, are going to develop these massive, what we call frontal thunderstorms. And the only reason, it's the same thing as a thunderstorm. The reason why we call it frontal is it's being basically pushed by some type of front. Okay. All right. Let us go on. And what I want to do at this point is, I do not want to bore you guys with the fronts. I think I'm just going to show you this 2-minute video that I've got anyways. Rather than showing you a bunch of slides. So let's go ahead and watch this. This is from our friends over at Embry-Riddle. They're going to talk about the 4 different types of fronts. There's a cold front, a warm front, a stationary front, meaning that no one's moving either way. And then we've got something called an occluded front, and the occluded front could be a cold front, basically a cold front occlusion or a warm front occlusion. And let's go ahead and take a look at this. And when we come back, we will discuss and talk about a few other things like virga and microburst. Go ahead and watch.
Air masses are large regions of air that have similar characteristics from the surrounding area. Air masses can form over places like warm tropical oceans, cold dry polar regions, or even dry deserts. As air masses move over different regions, they will gradually take on the characteristics of the new region and begin to change. As air masses move across the Earth, they will eventually run into each other. The boundaries between these two air masses are referred to as fronts. Fronts are labeled in reference to the relative temperature of the air that is approaching and replacing the existing air mass. There are 4 types of fronts: warm fronts, cold fronts, stationary fronts, and occluded fronts. A warm front occurs when a warm air mass overtakes an air mass of a colder temperature. Warm fronts usually move slowly, around 10 to 25 miles per hour, and have a gradual slope that will slide over the top of a cooler air mass and move it out of the area. Warm fronts usually contain high humidity and have more stratiform or layered clouds along the frontal boundary. Drizzle and decreasing visibility will be present as temperatures rise. Once the front passes, rain showers are possible, followed by a gradual clearing. A cold front occurs when cold, dense air overtakes warmer air. Cold fronts move faster than warm fronts, averaging 25 to 30 miles per hour, but can go as fast as 60 miles per hour. Cold fronts stay close to the ground and have a steeper angle than a warm front. They will move across the ground and lift existing air at a very rapid rate. This rapid upward motion will cool the air and form cumulus clouds, which could eventually develop into thunderstorms or even form a line of thunderstorms called a squall line. Once the front passes, the weather will clear and improve with general wind flow from the west-northwest. A stationary front occurs when 2 air masses meet, but neither one moves the other out of the way. Stationary fronts can have a combination of weather from both a warm and cold front. These fronts can oscillate, but will generally linger around for several days before one of the air masses pushes the other air mass out of the way. The last type of front is called an occluded front. Occluded fronts form when a fast-moving cold front catches up to a slower-moving warm front. Cold front will then lift up the warm front and eventually interact with the air that is in front of the warm front. This stacking of fronts can give rise to a variety of weather conditions, from fog to thunderstorms.
All right, so that is the 4 different types of fronts and subfronts associated with them. The next things we're going to look at are some things that we basically want to avoid. So this one that you guys see on the screen, I didn't like the image from the slideshow. This is called virga rain, and virga is very simply, it's just rain that evaporates before actually hitting or reaching the surface of the earth. We don't ever want to fly below this. It's going to be a sign of turbulence and also severe downdrafts. So if you see something like this, just go around it. Even though it looks perfectly clear and it looks safe, you'll be in for a world of hurt. These types of downdrafts can actually exceed most of our general aviation aircraft, so just watch out for that. The other one, going back to the slideshow here, I think this was on the virga rain one. I think that looks more like a microburst here in this image. So I'm going to move that. But basically, the next one we want to talk about is called a microburst. And a microburst is basically a huge burst of energy. And what it does is there's some cool videos on YouTube where there's just a ton of air and downdrafts. And what you'll usually see is as it hits the surface of the Earth, it's going to start to actually scatter outwards because it has nowhere else to go. And the important thing with a microburst is really when you're coming in for takeoff and landing, these cells and these systems are so dangerous. Even to there's a lot of commercial airliners that have been lost due to microbursts, and they're not the most predictable thing in the world. There are microburst detectors in certain locations throughout Texas and where we know that they primarily exist. But the big thing is that a microburst has so much energy, and the downbursts are so significant that even commercial airliners in turbine-powered aircraft do not have the capability to continue climbing. Those downdrafts could exceed 6,000 feet per minute, and they're significantly strong. Now, what ends up happening in a microburst, though, and the reason why it's dangerous, primarily going to be on landing, and the reason why we never take off into a thunderstorm and everything else is really because of the information that we've learned from a microburst. So this is kind of the wind pattern, and very simply, if you encountered a microburst or anything like this, and this glide slope is basically what the pilot, this red line basically represents what the pilot should be flying. And what you're going to realize is the very first thing that will happen in a microburst is you will actually get a headwind, okay? Because all this air is coming down, it basically starts to deflect outwards, right, in both directions. And really, the first thing that we start to experience here will be a headwind, and then eventually that will actually switch sides, because once you get through the halfway point, it's actually going to turn to a tailwind. So when you experience a headwind, you're basically kind of getting an artificial increase in a bump, and you're going to start to actually balloon a bit. So you'll see in position X, the pilot is already starting to balloon. They recognize what's going on. They're higher than what their intended approach should be. And traditionally what pilots will do in the Y position in the center there is, because you're high, the solution for that is to remove power and point the nose down. And the mistake being is that when you start to remove power, you start to go to a lower airspeed. And when you start to switch from a headwind to a tailwind, that's significant wind shear. And very simply, what will end up happening is that you will start to move, you'll get back to your glide slope where you should be, your approach altitude. But because you're losing all of your airspeed, you're actually going to stall the airplane before you even get to the airport. Or you could just get pushed down enough by the downdrafts and just hit the ground, okay? So traditionally what will end up happening is that you might experience wind shear, and all you're going to do in this case is you might see a test question in the near future here that's going to ask you what is the total wind shear. And very simply, if you're flying along, and let's assume that there's no headwind or tailwind right here, but as soon as you hit the front part of that microburst, and the microburst is 25 knots of headwind, okay? And then you get to the midway point, and that headwind shears to a tailwind, and the tailwind is equally as strong, and it's 25 knots, and I'm going to call it tailwind. All you do to figure out what the total shear is, right, is add the difference, or add up the totals. 25 plus 25 means that there's 50 knots of shear in that system. Okay, 50 knots of shear in that system. So let's see here. So hopefully, like I said, this is more of a learning point. I mean, if you guys ever see something like that, do you really think that you guys are going to be flying on the approach to an airport? They can come out of nowhere, but you know, our detection equipment is much better than it used to be in the 60s and 70s when a lot of these accidents happened. And the reality is that very few general aviation accidents, you know, recently have occurred in this type of situation just because of knowledge, right, and education on the topic. All right, the other thing too, we've been talking about all of these thunderstorms, and the next thing I want to kind of talk to you guys about is just kind of avoiding them. So number one, we never, ever fly in thunderstorms. What does not matter whether it's general aviation aircraft or if it's an airliner, we do not intentionally fly into a thunderstorm. The rule of thumb is to basically stay, I think I said 25 miles earlier, it's 20 miles from the FAA in all directions from the actual cell of the thunderstorm. I would not do what the author is representing this pilot doing. I would not try to fly 20 miles on either side in between cells like that. I do not know if they are potentially converging, and I don't know what the rate of convergence is. I mean, they could be coming together or they could be going apart. Who knows? The other thing too is that if you wanted to fly over the top of a thunderstorm, assuming you may have, you know, hit the lotto and you got your $50 million business jet, you can cross over the top of a thunderstorm. And the recommendation there is that for each 10 knots of speed, in terms of how fast that thunderstorm is moving, you basically would cross it at least by 1,000 feet higher than whatever the top of that cell is. So if this cell was moving at 10 knots and the top of the thunderstorm was at 50,000 feet, you'd want to cross it at 51,000 feet. Okay. In the event you accidentally went into a thunderstorm, I'm hoping that's never the case with private pilot students. Very simply, first thing you want to do is slow down. You want to get to your not your VG speed, but your VA speed, your maneuvering speed. So that way you're going to be experiencing some pretty severe, if not extreme turbulence, and you need to protect the structure of your aircraft. So by slowing down, that number one, that will definitely help. Number two, what you want to do is if you have any type of anti-icing equipment, try to turn it on. For most of us, that's just pitot heat and also defrost. That'll avoid us from icing up. And it really depends on the temperature outside. But if you're below the freezing level, you should be good. Or if you're above negative, if you're basically below -15, or very close to the freezing level, you're usually that's where it's going to become a concern. After that, turn up all your cockpit lights. Keep your eyeballs inside. Use those 3 hours of instrument training you guys will get, and that's really to basically lessen any effects of lightning blindness. Then what you're going to do is you're going to use your instruments, preferably make a 180-degree turn to go exactly out the same way you came in, and you can use your turn coordinator. And remember, on that turn coordinator, all you're going to do is do a standard rate turn, right or left, for 1 minute, and continue flying out back from where you came from. Okay. All right, so let's go ahead and take a look at a microburst question here, and then we'll move on to mountain wave activity. An aircraft that encounters a headwind of 45 knots within a microburst may experience a total shear across the microburst of, is it 40, 80, or 90 knots? %, like Josh said. Not quite there, Joshua, but one of these we'll get. All right, there's about 60% of the class. All right, guys, let's go ahead and take a look at it. We have about 88% of the class with the correct answer. Nobody said A, which was good. Some people need to break out their calculator that said B, but very simply, we have the headwind, and if you just remember kind of a microburst going out in both directions, right? This would be our headwind if this is our airplane moving this way, and then it would shear to a tailwind. We know this is going to be 45 knots, and the opposite side would also be 45 knots. And it's because if it goes from a headwind to a tailwind, it's going to be, you're going to lose that. So all you're going to do is basically add those values up together, and that is why we're coming up with 90 knots. 45 plus 45 is 90. Microburst cycle is going to be relatively short, so it's usually like anywhere from like 15 minutes, somewhere around 15 minutes, plus or minus. All right, the next one we're going to look at is mountain wave activity, or MWA. Very simply, this is going to occur in more mountainous regions of the country. So primarily if you're in the West Coast, or if you're potentially by the Appalachian Mountains, this is where you're most likely to see this. Mountain waves, they produce these significant downward drafts on the backside, or what we call the leeward side of the mountain. And the downward drafts can actually exceed most of our maximum climb rates of most aircraft, including business jets out there as well. So you can imagine the business jet has all of this excess thrust and power, and if they can't climb out of it, then you might be in trouble with your 160 horsepower engine. There's a couple things that will give us some visual clues, but like you see here, we've got lenticular clouds, which is like a lens-shaped cloud. And if you see a lenticular cloud over the top of a mountain, like if anyone here is from the Pacific Northwest, I used to see them a lot over Mount Rainier. If you see a lenticular cloud, that is your indication that there is winds of 50 knots or greater going over the top of that mountain. But the clouds, regardless of if there's clouds or not, whether they're lenticular or rotor, it doesn't have to be there for basically mountain waves to exist. And mountain waves could extend up to 15 miles beyond the backside of the mountain. And very simply, in the event that you are stuck here, and this is where the downdrafts happen, the number one mistake that people make, and the reason why they get into accidents, is they assume that the downward draft is associated with just the position that they're currently in. And if this was the ridge line, let's say, the very top of the ridge, what they do is they are right here and they're experiencing severe downdrafts. So then they just make a turn and they continue following the ridge, and they keep following it and keep following it, thinking it's going to be better, and it's isolated. And the reality is that we have all of this air starting from the windward side to the leeward side, and it's continuing to push them down. And that's what most of the NTSB accident reports that I've read kind of come to the conclusion. And if you are trapped in this position, your best solution is to go towards the center of the valley, where you can get further away from those downdrafts rather than kind of staying along that ridge line right there. Okay. Now, glider pilots, they love this stuff. This is actually things that they look for because they can count on knowing where the updrafts are and the downdrafts within mountain waves. So certain pilots do actually utilize this for knowledge. Now, those lenticular clouds, they come in different variations. They're not always perfectly lens-shaped, but very simply, you've got the cirrocumulus standing lenticular cloud. Those are a bit higher up. You have, which are, remember, cirro meaning high, alto meaning middle. So these are the altocumulus standing lenticular clouds. And then we also have rotor clouds, and they're not as pretty as what the authors show. They're not perfectly circular, but the rotor clouds are usually closer to the ground than any of the others. And then with the any of these, you can experience them at all altitudes. Airline pilots, as we cross the Rockies a lot of times in the past, I've seen them, and at altitude, they're not that big of a deal. It's just kind of increases and decreases of airspeed, basically airspeed fluctuations that you have to manage at those types of altitudes. Okay. All right. So here is your only question dealing with whatever the topic is. An almond or lens-shaped cloud, which appears stationary but which may contain winds of 50 knots or more, is referred to as, is it A, an inactive frontal cloud, B, a funnel cloud, or C, a lenticular cloud? Interesting thought, Larry. All right, there's the first third of the class in. Not quite 100%. All right, there's about 70% in. Awesome, Shane. That's a lot of work for 3 days. All right, almost there. Just waiting for a few extra people here. All right, looks like we got them. All right, so not quite 100%. Basically, almost 96%. Almost 96%. So a couple of folks on other topics here. All right, so correct answer, anytime that we're looking at any type of like almond or a lens-shaped cloud that's basically, just hovering and sitting there, That means, number one, we call those lenticular clouds because of their shape, but that's also going to indicate that there is significant wind, usually greater than 50 knots. All right, let's push on. And the last thing that we want to cover in the weather theory is going to be your fog. So very simply, there's several different types of fog that we're going to run through. And fog is not considered a cloud. It's just basically, it has to do with your visibility. And a lot of times fog is going to, well, pretty much every single time, fog is going to reduce your forward visibility. And what you guys will end up seeing is in our weather reports, we always talk about visibility in terms of your horizontal visibility in statute miles, meaning how far can you see down the runway, for example. But you'll also see something called vertical visibility, and that's basically, you know, if you're standing there on the ground and you look straight up, how far can you see straight up? And a lot of times you actually, you're kind of in a fog bank, if you will, and if you look straight up and the fog bank is relatively shallow, sometimes you can see blue sky and the sun out above it, okay? So it just depends on what type of fog it is and how persistent it happens to be. So first one we're going to talk about is called radiation fog. This is fairly common. It's produced over a land area where radiational cooling reduces the air temperature to at or below its dew point. Radiation fog is relatively shallow, and ground fog is basically a form of radiation fog that's confined to near ground level. The three factors that basically favor the formation of radiation fog are a shallow surface layer of relatively moist air beneath a drier layer. We have clear skies and then light surface winds. If it's very windy, the radiation fog is not going to actually form or develop. Advection fog is very common in the Bay Area if anyone is from there or is visited, where we see these pictures from, or basically along the coastal areas as well. This is going to form when we have moist air, which moves over a colder surface, and then the subsequent cooling of that air to at or below its dew point. You're going to hear that term quite frequently. It's most common along coastal areas, but it can move pretty far inland over continental areas. So this fog could actually come 20, 30 nautical miles off the coast as well. The fog frequently forms offshore as a result of cold water and then is carried inland by the wind. It remains over the water for weeks, and then it advances over the land during the night and then kind of goes back and forth. But just keep in mind that it can move in rapidly regardless of day or night. And this is a type of fog that's usually more extensive and persistent than radiation fog as well. Next one we've got is called steam fog, and this occurs when we have very cold air which moves across relatively warm water, and then we've got enough moisture may evaporate from the water surface to produce saturation. As a rising water vapor meets the cold air, it immediately recondenses and rises with that air that is being warmed from below. This is going to be most commonly observed on cold autumn mornings over lakes and streams and over the ocean during the winter when the cold air masses move off the continents and the ice shelves. What you're kind of seeing here is that light steam fog in the image on the right. And just keep in mind that this will create turbulence, or what we call an unstable air. And in the event you fly over it, so if you are flying maybe in a seaplane over this, or maybe there's a small stream or lake prior to or basically on the approach end of your airport, just realize that you might or you want to expect convective turbulence while flying through it or over it. The last one that we've got is called frontal fog. Now the other term for this is precipitation-induced fog. That's actually an older term. Frontal fog is going to occur when warm, moist air is lifted over a front. Clouds and precipitations may form. Instead of may, I'll probably say most likely. If the cold air below is near its dew point, evaporation from the precipitation may saturate the cold air and form fog. Frontal fog can become quite dense and continue for an extended period of time. This will cover large areas, and this has the potential to basically completely suspend all air operations. So if something like this happens, this will basically shut down an entire airport, and it could be like that for a significant period of time. All right, just checking the time here. All right, so I can introduce this topic quickly, and then what we're going to do is we'll spend more time on it. I know you guys are all looking forward to METARs and TAFs here. We'll do those coming back on Monday, okay? So That basically wraps up everything that we wanted to cover for aviation weather. I'll do a quick intro for 5 minutes here on what we're supposed to be covering for Monday, which is really the practical side of everything that we need to do. And very simply, this is really all about, where are we supposed to get weather briefings? Who are we supposed to talk to? And then how are we supposed to actually utilize the information that we're getting from these different weather sources? Okay. So you, as I've said before, will not learn about every single, chart that's available to you. There's only a few that you need to know. A couple things that I will point out, though, is there is this flight category definition. Does everyone remember what is basic VFR? What is basic VFR? Do you guys remember what that is? So many lessons ago. Heard me use that term on day one. Probably also heard me use it in airspace the first week and regulations the next week. And this is one that you want to kind of take a note of. This is a number that you basically need to memorize. So a little bit higher, a little bit lower actually. Matt S, you're the first one to get there. So basic VFR is 3 statute miles of visibility. And then it's basically going to be and or 1,000 foot ceiling. Okay, so you usually saw me write this as 3 statute miles and 1,000, right? Anything less than 3 statute miles visibility and or less than 1,000 foot ceiling is the equivalent of IFR conditions. Okay, that's what we call basic VFR. Now a ceiling is defined as the lowest of the overcast or broken layer. Okay, so the ceiling, you'll see that these are different cloud coverage symbols. We basically have clear skies, sky clear, SKC, and then we've got few, scattered, broken, and overcast. And the only two we really care about for the purposes of a ceiling is broken and overcast. So broken, this you can kind of think of it like a pizza pie, pretty much 75%-ish, and there's an exact number there, of the sky is covered with clouds. Overcast is a solid cloud layer, and that's what basically is an overcast layer. So when we're talking about the ceiling, it is the lowest of the broken or overcast layer. Okay. The reason why I've got this slide up for you guys is I want you guys to realize that the weather folks use a little bit different definitions. For the purposes of pilots and for the purposes of regulations, basic VFR is the numbers that are on the screen that I just wrote down. For the weather folks out there, what they do is they basically categorize it as low IFR, IFR, marginal VFR, and VFR. And the reality is that we as pilots only have 2 flight regulations. You are either operating visual flight rules or you are operating under IFR flight rules or instrument flight rules. You're not operating under low IFR or anything else. So I just want to point that out to you guys so you guys aren't confused. Now the weather folks are basically going to define low IFR as anything below 500 feet and less than 1 mile. You'll notice they'll basically categorize it as a pink category. IFR, which is really true IFR, basically anything less than 1,000 foot ceiling and less than 3 statute miles, I would agree with that, is going to be instrument flight rules. Marginal VFR, which is a blue symbol, is between 1 to 3,000 feet and 3 to 5 statute miles. So basically what we have here is everything from marginal down is going to be considered VFR, okay? Including the VFR. They're saying VFR is greater than 3,000 feet and greater than 5 statute miles, which is, definitely better than the basic VFR legal minimums that we need to have, okay? So just keep that in mind, that when we are looking at these things, understand the definition of a ceiling is the lowest of the overcast or broken layer, and basic VFR is defined as 3 statute miles and 1,000 foot ceiling, okay? Now, what these colors basically represent is just a quick way for you, the pilot, to basically figure out what is going on. And just like I showed you guys before, if you guys go to SkyVector or any of these other websites out there, you will inevitably see all of these different color codes on your charts, okay? So I'll just turn them on real quick. I'm trying to see if there's like an area in which you guys just have bad weather. I haven't really been looking at the weather recently. I think there's a cell up in Michigan, it looks like. So if you were to basically turn all these little things on, you would basically see, you know, the different color codes shown. Okay, and let's see. I think I've got a few here. So very simply, this is just for planning purposes. You can see on each one of these, SkyVector does it a little bit differently, but same thing will apply. It's called text weather that you could turn on. And some of these are green, which are telling you it is VFR. Some of these are red, which is telling you that it's IFR. Some are blue, which is basically that marginal VFR. But keep in mind, all of these color codes are based upon the NOAA definitions of flight categories that I just showed you guys right here. Okay, so take them with a grain of salt. You always want to read whatever the actual weather is, the textual weather, and make sure that you understand it before you kind of continue on. The other thing too is that when we get into METARs and TAFs, honestly, this is really what it comes down to. This one's actually kind of funny, right? So you're going to realize that the shorter the METAR is or the TAF is, the more likely that you're going to fly. The longer that it becomes, the less likely that you are to fly, just because there's more complicated weather going on at any given time. I mean, it's almost like it is almost, I would say this is pretty much true to life here, okay? So what we're going to be doing on Monday, and we're not going to have time tonight, is we will be talking about METARs, which is really the first point, okay? And a METAR is just a meteorological aviation report. So it basically provides the current weather, and it's updated every 55 minutes past the hour. Now what you're going to see here is all of this codification on the screen here, right? We have all these different little abbreviations and plus symbols and, you know, all sorts of things that probably look new to you. What I would encourage you guys to do is right beneath this live stream here, there's a document that basically says a METAR decoder. It's a 2-page document. And what it does is it will basically help you to decode METARs and TAFs, and it gives it to you in the exact same order that they're presented. You'll notice that the METARs and the TAFs, they're always really, the information is always in the same location. It's really kind of filling in the blanks. And then, of course, it depends on the system. How many different bells and whistles did the municipality have, or how much money did they have to put in their weather system or sensors? Sometimes you can see some crazy information at the end, like how much rain did you accumulate in the last 3 hours versus 6 hours versus 9 hours, right? And, you know, it's kind of overkill. The big thing that I'll tell you guys, though, is that the main weather codes, and then we'll go after this, that you kind of want to pay attention to would be some of these that you're going to see. Number one, we always start with a qualifier. The qualifiers are over here, and it's basically just a minus or a plus. So very simply, if I said RA, okay, and RA is rain. If I don't have a qualifier here, RA is basically moderate rain. If I say minus RA, that's light rain. If I make that into a plus, that's heavy rain, okay? The most common ones in terms of the weather codes and things that you will see, you'll not have to memorize all these, but I'll point out the most common ones, will be showers, SH, thunderstorm, TS, freezing, FZ, drizzle is DZ, rain is RA, snow is SN, hail is, for the Midwest folks out there, GR. We also have our baby rain. So just think of mist as baby rain, very small rain droplets. Fog, FG, for all of us in California. Smoke is FU, which comes from, is it fume or fume? I've never looked it up. It's a French word for smoke. The other ones are haze, and that is pretty much the most common ones. Going on to the remarks, a lot of times the METARs will have some type of remarks added at the very end that will give you some additional information on it. So a common one that you're going to see is if you see CIG, that means that is the equivalent of ceiling, okay? And then if you ever see a V anywhere, okay, if you see a V anywhere, you'll see it also here as well. That means that it is variable. Something is variable, meaning that in this case, the first one, ceiling is variable between 1,400 and 1,900 feet, okay? Other ones that you're going to see is RAB and RAE. RAB is rain began and RAE is rain ended, and then it will tell you the time past the hour that it began or ended. Or if it's still going on, you might just have an RAB with a value past it, which is going to tell you that it started, but it hasn't stopped at this point. If you have very shifty wind, like I showed you guys before, we would look at this one right here, which is basically wind, and we've got that V there, and it means variable. So the wind is variable between 270 to 330. If it's very, very windy and it has if the municipality has the extra equipment, it might tell you the peak wind, right? So the peak wind here, the value is at the very front, which is telling you the direction and the velocity, and then it will tell you the time past the hour. The direction is 330 at 48, and it occurred 22 minutes past the hour. And then the last two basically deal with pressure. And pressure is either rising rapidly or it's falling rapidly, which would basically tell you that there's probably a front that's moving in. And the easy one to remember is the bottom one here, which is fresh FR, which is falling rapidly, and the opposite one is SR. They should have just used RR, but pressure is rising rapidly as the SR version of that. Okay, so that is what we're going to be looking at when we come back on Monday, and then most of the codification that you guys see here is going to extend into what we're going to take a look at for our TAFs as well. So TAFs are basically a forecast instead of the weather, the current weather. A TAF is basically a forecast over either a 24 or 30-hour period using kind of the same terminology, and we'll go ahead and take a look at that on Monday. All right, everybody, so that basically wraps up everything that we wanted to cover for today's class. As we kind of push on, remember, if you want to take or basically attempt today's lesson quiz, you're more than welcome to take that college try. If you want to wait until we basically wrap up the rest of the material, you can always wait until we get to that point. So it's not going to hurt you if you take the lesson quiz in 2 days from now. Not a big deal. In addition to that, we're also going to try something new just for this week. So with the Q&A, the Q&As are, because I have a class right after this, we're going to attempt to do the Q&As basically using the moderators and also our tech team. So if you have any questions, feel free to just throw them in the chat. And we're just going to see if this can increase the efficiency a little. We're going to do a little bit of a test over the next couple days and see if this works or not. But other than that, if you have any questions that we weren't able to answer in the meantime, remember, if it's aviation related, you have the Facebook group, which is a great opportunity. Very, very easy to find a quick answer there. You have Ask a CFI, which is on our website. Remember, when you log in, you can basically throw in a question. It's like a discussion forum. You can also see the hundreds of questions that students have basically submitted and we've answered. We typically check those, and I review those 2 to 3 times a day. In addition to that, if you have a technical question, I know Travis and the tech team is going to remain on as well with you. If there's something that they weren't able to answer, you might need to open up a technical help, or basically a help desk ticket that is. Remember, in the lower right-hand corner of your screen, there's that little yellow headset. Just click on that, and you can click on Submit a Ticket to start that process. Just be as specific as possible. So with that, I hope you guys are enjoying the classes so far. What we'll do here is I am going to go ahead and sign off and prepare for my next class. Moderators and the IT team is going to stick around and answer any last-minute questions that you have. We'll keep the chat open, making sure everybody's questions are answered. And I will see everybody in about a day and a half, 2 days for our next lesson. Take care, everyone. Stay safe, and we'll see you later.
SIGMET.